Currently soaring over 29 million miles above the surface of Mars, an object streaks past in a manner that defies expectation. An entity that shouldn't be here, moving at an astonishing 210,000 kilometers per hour. It's not just a comet outgassing lazily on its journey. It's a visitor that challenges our understanding, belching carbon dioxide at a rate 8 times that of water, with a ratio so bizarre it sits 6 standard deviations outside what we consider normal. Its size, too, remains a mystery, estimates fluctuating wildly from 300 meters to 5 kilometers. And the very statistics surrounding its detection, our third confirmed interstellar object, make some scientists deeply uncomfortable. Tonight's data could settle this enigma once and for all, or perhaps it will deepen the mystery, making the universe seem even stranger. What are the orbiting spacecraft around Mars witnessing as this enigmatic traveler blazes past? What clues will the Hubble Space Telescope gather at perihelion in just 3 weeks? And if, after tonight, the numbers still refuse to add up, what implications does that hold for our broader understanding of the cosmos? Before we delve into the unfolding story, take a moment to reflect. Where are you watching from right now? Share your location in the comments. I'm eager to hear your thoughts. Do you believe we're alone in observing this, or could someone or something else be watching us too? Part 1. The flyby that will shock the world. It's October 3rd, 2025. Right now, as you listen, something ancient and utterly foreign is hurtling past Mars at speeds that make our fastest rockets seem sluggish. Its name is 3I Atlas, and it's about to come closer to the red planet than most of us will ever understand. All around the planet, multiple spacecraft equipped with sophisticated instruments are trained on this mysterious visitor. And for good reason. This isn't simply another comet. This is only the third confirmed interstellar object to pass through our solar system in recorded history, and it exhibits behaviors that unsettle astronomers deeply. Let me set the scene. In 2017, a strange object called Oumuamua zipped through our neighborhood, leaving behind a trail of questions. It accelerated in ways that no comet should, looked like either a cigar-shaped body or a pancake, depending on who you asked, and vanished before scientists could get a proper look. 2 years later, in 2019, came 2I Borisov, which behaved like a textbook comet, a visible coma of gas and dust, acting just as comets are supposed to. That discovery brought relief. The universe made sense again, or so we thought. But then, on the 1st of July of this year, 2025, the Atlas Survey, a sort of cosmic early warning system designed to alert us to objects that could threaten or bewilder us, spotted something new, something moving in a way that didn't belong. Not broken, not malfunctioning, but fundamentally out of place, on a hyperbolic trajectory, meaning it's not gravitationally bound to our sun. It has come from somewhere beyond the limits of our solar system, traveling at a speed that makes it clear. This object is not native to our neighborhood. It's an interstellar visitor. And tonight, as it approaches Mars, it might just change everything we think we know about our cosmic surroundings. It originated from a distant corner of the galaxy, drifting through the cosmic darkness beyond our solar system's reach, merely passing through our neighborhood in the vast expanse of space. We have designated it as 3I Atlas, with the I standing unmistakably for interstellar, reflecting a milestone in human history. Our recognition that visitors from other star systems now warrant their own category within our astronomical catalogs. This naming convention signifies that we've reached a point where the universe's wandering travelers are becoming part of our systematic understanding, not just rare anomalies. And now, here is where the story takes a fascinating turn. Observations from the Hubble Space Telescope have provided us with an upper limit on the size of this object's core, its nucleus, placing it at approximately 5.6 kilometers across. To contextualize that, it's roughly comparable in size to the asteroid that caused the mass extinction of the dinosaurs, making it an object of substantial scale in cosmic terms. But crucially, this measurement is just an upper boundary. The actual size could be considerably smaller. Estimates suggest it might be as tiny as 320 to 440 meters in diameter, a difference of over an order of magnitude. This enormous uncertainty arises from a fundamental limitation. We cannot observe the nucleus directly. Instead, it is concealed within a dense cloud of gas and dust, what astronomers call a coma, that surrounds it. This veil of material makes the object appear larger than it truly is, complicating our efforts to determine its true dimensions. This predicament leaves us somewhat in the dark, a less than ideal position when trying to distinguish whether this object is a natural celestial body or something more artificial. But the size conundrum isn't the only perplexing aspect. There's also the matter of non-gravitational acceleration, subtle forces acting upon the object that don't align strictly with gravitational expectations. When comets approach the sun, they heat up, releasing gases that act like tiny rocket thrusters, nudging them gently but measurably. This phenomenon has been observed before, most notably with the interstellar object known as Oumuamua. Its unexpected acceleration, despite the absence of visible outgassing, sparked widespread speculation about artificial origins. In contrast, 3I Atlas displays a very prominent and active coma, with the James Webb Space Telescope observing vigorous outgassing of gases, an unmistakable sign of sublimation. Yet, intriguingly, the object's non-gravitational acceleration remains minimal, almost negligible. The calculations based on JWST's data suggest that if the outgassing reports are accurate, the object must be incredibly massive, around 33 billion tons, with a minimum diameter of about 5 kilometers. That's a colossal mass for something of that size, and the math doesn't seem to fit neatly. The apparent weight and the observed activity are at odds, prompting astronomers to consider alternative explanations. Tonight, as 3I Atlas passes approximately 18 to 19 million miles from Mars, about 29 to 30 million kilometers in the metric system, our orbiting spacecraft are watching intently. Come December, it will swing by Earth at a distance of roughly 269 million kilometers, giving us another close-up opportunity. Importantly, it's crucial to emphasize that there is no threat to our planet from this object. It remains safely distant, with nothing indicating an imminent collision. However, this encounter with Mars is invaluable, because it offers our best chance to investigate the object at close range. Multiple spacecraft equipped with sophisticated instruments are observing, capturing data that may unlock its secrets. One of the most compelling findings is the chemical composition of its coma. The JWST observations reveal a dominance of carbon dioxide with a CO2 to H2O ratio of about 8:1, an extraordinarily high proportion for any comet encountered so far. Typically, comets are rich in water ice, the most common volatile component. But this alien body appears to be belching out carbon dioxide at a rate that suggests something unusual is happening, almost as if it's trying to terraform Mars in reverse. In addition to CO2, the spectrometers detected water vapor, carbon monoxide, carbonyl sulfide, and water ice particles, painting a complex picture of an active, chemically distinctive object. The ratios are all out of sync. Imagine discovering a bird that, despite quacking, boasting feathers, and waddling like a duck, somehow tastes like beef. Technically, such a creature could exist, but it would raise immediate questions about your classification. You'd want to double-check your taxonomy, ensuring your identification isn't mistaken or misleading. And then there's Avi Loeb, a prominent astrophysicist from Harvard University whose reputation for challenging conventional thinking has made him both influential and controversial. For those unfamiliar, Loeb has carved out a second career by openly entertaining the possibility that some of these interstellar visitors might not be natural objects at all, but could in fact be artificial in origin. He proposed that the acceleration observed in Oumuamua, the first recognized interstellar object, might be explained by a light sail, a thin reflective membrane propelled by radiation pressure from the sun. Though most of his colleagues remain skeptical, Loeb has now turned his attention to the current interstellar visitor, known as 3I Atlas. To quantify these suspicions, Loeb developed what is called the Loeb scale, a 10-point ranking system designed to gauge the likelihood that an interstellar object is an alien technology. At 0 on this scale, the object is definitively natural, a routine celestial body with no signs of artificial origin. Conversely, a score of 10 indicates that the object is a confirmed alien craft, potentially dangerous and warrants immediate concern. In early August, speculation among some circles assigned a rating of 6 out of 10 to 3I Atlas, suggesting a 60% confidence level that it might be a product of extraterrestrial engineering. As more data poured in, Loeb himself revised that rating downward in a detailed Medium post, adjusting it to 4 out of 10. While this still leaves room for suspicion, it indicates a reduced but persistent possibility that the object could be artificial. Whether you accept his framework or not, that number has sparked a heated debate across the scientific community and beyond. At this moment, as the Mars-bound spacecraft sweep their sensors across the passing object tonight, 3 competing narratives have emerged to interpret the data. First is the orthodox view, that 3I Atlas is merely a highly unusual comet, an exotic but ultimately natural visitor from another star system. It exhibits chemistry that deviates from typical solar system comets, but remains within the bounds of natural phenomena, perhaps a product of formation in a different environment. Second is the artifact hypothesis, suggesting that the object is a constructed device, perhaps a probe or a remnant of technology sent from an alien civilization capable of observing us as we observe it. This idea challenges the assumption that all interstellar visitors are purely natural, raising provocative questions about what we might be missing. The third scenario, perhaps the most unsettling yet compelling, posits that 3I Atlas is a fragment, an outlier, a shard from something that was destroyed far away, billions of kilometers from any star. It could be part of a debris stream, a trail of shattered relics resulting from a catastrophic event that occurred eons ago. This debris might be remnants of a planetary collision, a star's tidal disruption, or some other violent cosmic upheaval. If the coma we observe is genuine outgassing, why is the push from this gas so weak? Why does the chemistry appear so skewed? Why now, after centuries of sky watching, are we only seeing such objects in recent years, 3 in just 8? Tonight, as 3I Atlas makes its pass by Mars, we might finally start uncovering answers. Or perhaps we'll only deepen the mysteries, generating new questions that challenge our understanding of the universe. Part 2. The data from Mars. These silent witnesses. Let's examine what's happening right now. The European Space Agency has 2 orbiters in position to observe this encounter precisely. The first, Mars Express, has been studying the red planet since 2003, providing a long history of detailed data. The second, the ExoMars Trace Gas Orbiter, launched in 2016, is a newer, more sensitive instrument designed to analyze atmospheric composition with exceptional precision. Both are scheduled to monitor 3I Atlas from October 1st through October 7th, with the closest geometry, meaning the best observational alignment, occurring today, October 3rd. This isn't merely coincidence. The vantage point provided by orbiting Mars is an extraordinary asset for this kind of observation. When trying to scrutinize an object traveling at interstellar velocities, every angle matters profoundly. From Earth, our perspective is limited to a single vantage point, one viewing angle that restricts the detail and depth of understanding we can achieve. However, from Mars's orbit, positioned about 225 million kilometers away, we gain a different, more insightful perspective. This multi-angle view allows us to observe the object's form, its jet activity, and rotational behavior with a clarity impossible from our terrestrial vantage point. As these spacecraft observe and gather data, they are focusing on specific questions. From our vantage point here on Earth, Mars currently lies approximately 225 million kilometers away, a distance that varies depending on the relative positions of the two planets within their respective orbits. This separation means that observing a passing object from Mars provides a fundamentally different perspective, one that can uncover details hidden from our Earth-based vantage point. To illustrate, the difference is akin to the contrast between watching a car drive past you on the street and viewing it from a drone hovering overhead. The latter vantage point reveals angles and features that simple ground-level observation cannot, and this principle applies equally to studying interstellar visitors like 3I Atlas. When multiple observation points are spread across millions of kilometers of space, our understanding of such objects becomes exponentially clearer. These diverse viewpoints allow us to decipher a host of properties, shape, jet directionality, rotational behavior, that would remain ambiguous or impossible to interpret from a single perspective. So what exactly are the Mars orbiters aiming to measure during this fleeting encounter? Let's unravel this in straightforward terms that don't require advanced degrees in astrophysics. First up is spectral analysis. This involves breaking down the light emitted or reflected by the object into its component wavelengths. Each molecule interacts with light in characteristic ways, absorbing specific wavelengths and emitting others. So by examining the spectrum, scientists can identify the gases actively outgassing from the nucleus. The James Webb Space Telescope, JWST, using infrared spectroscopy, previously detected a bizarre dominance of carbon dioxide in the coma. The current Mars instruments will be checking whether this spectral signature remains consistent, or if it evolves as the object moves through different thermal environments, getting closer to the sun, heating up, and possibly changing its outgassing patterns. Second is the measurement of reflectivity, or albedo. This describes what percentage of sunlight the object reflects versus absorbs. A very dark surface might indicate carbon-rich organic compounds, perhaps akin to a burnt marshmallow drifting through space, while a brighter surface suggests pristine ice. Analyzing albedo offers clues about the surface composition and also reveals whether the surface has been altered by radiation exposure over millions of years in interstellar space. Such radiation processing can darken or change the surface, affecting how it interacts with sunlight. Third, scientists examine rotational flicker, how the brightness of the object varies over time. If the object is tumbling or spinning, different facets will face us at different times, causing periodic fluctuations in brightness. By analyzing this light curve, we can infer the shape, whether it's spherical, elongated, or irregular, and determine if it's rotating smoothly or tumbling chaotically, which might suggest a history of trauma or disruptive interactions. For instance, a stable, predictable flicker pattern might indicate a compact, well-formed nucleus, whereas erratic variations could hint at a fractured, battered object. Fourth is the shape and behavior of the coma itself. Gas and dust don't simply puff off uniformly. They often emerge in focused jets, erupting from specific surface locations where ice is most exposed or subsurface pressure has built up. JWST has already observed an asymmetrically shaped coma, indicating uneven activity. The Mars orbiters will track how this asymmetry changes as the sun's heating angle shifts during the flyby. If the jets respond predictably, intensifying or shifting with the sun's position, that supports a natural thermal-driven process. Conversely, if the activity doesn't respond as expected, it could open the door to alternative explanations. Fifth, the observers will monitor jetting behaviors, sudden outbursts where activity spikes unexpectedly. These can occur when volatile pockets beneath the surface burst through, triggered by thermal stresses, rotational forces, or impacts from smaller particles. Detecting whether such outbursts happen and their characteristics offers insight into the internal structure and composition of the object, revealing whether its activity aligns with natural cometary processes or something more anomalous. However, amidst all this, there's a significant challenge. Even at its closest approach tonight, 3I Atlas remains incredibly distant from Mars by observational standards, tens of millions of kilometers away. This vast separation limits the resolution and detail achievable by our instruments, meaning that while we can gather valuable data, the object will still be faint, fast-moving, and surrounded by a diffuse coma. These factors complicate precise measurements and require careful interpretation. Despite the state-of-the-art technology aboard the orbiters, we must acknowledge that the distances involved impose fundamental constraints on the granularity of the data we can obtain during this brief flyby. Currently, the object is situated tens of millions of kilometers away from us, so far that its own size might only amount to a few kilometers across, possibly even less, cloaked within a faint diffuse cloud of gas and dust known as a coma. This makes it inherently difficult to observe directly. It appears faint and moves swiftly through space. Moreover, the orbiting spacecraft around Mars face a significant limitation. Their observational time is restricted because they are primarily designed to study Mars itself, not transient visitors passing through the solar system. Consequently, if these orbiters do not detect something during their brief windows of observation, it does not necessarily mean that nothing is there. The signal might simply be too weak, or perhaps the timing of their observations did not align with the object's closest approach. This challenge underscores why integrating multiple observational perspectives is critically important. The Hubble Space Telescope, with its exceptional resolution, can distinguish the tiny nucleus of the object from the surrounding coma more effectively than almost any other instrument we have in space. Meanwhile, the James Webb Space Telescope, with its advanced infrared capabilities, can analyze the gas and dust's molecular fingerprints, revealing the chemical composition of outgassing materials with exquisite sensitivity. The Mars orbiters contribute by providing data on how the object's position and shape change over short periods, offering insights into its geometry and trajectory. Combining these three sources of data forms a powerful triangulation method, enabling us to refine and constrain our models of the object's nature. For instance, a model that aligns with Hubble's size constraints but conflicts with JWST's chemical data can be discarded, just as a model that explains JWST's observed carbon dioxide dominance, but predicts a coma shape inconsistent with Mars. Expresses observations would be called into question. Science progresses through this process of triangulation, building a three-point perspective that helps eliminate false leads and hones in on the most plausible explanations. At this stage, we're establishing a highly effective observational triangle, leveraging the strengths of each instrument to understand the object better. Next, consider what anomalies in this data might look like, signs that something unusual is occurring. One potential indicator is an unexpected flickering pattern in brightness not consistent with a simple rotation. Such irregularities could suggest a complex, irregular shape, a natural formation perhaps, but one that would certainly pique scientific interest. Alternatively, anomalies might manifest as off-axis jets, streams of gas and dust erupting from the object in directions that do not align with what would be expected based on solar heating. These could reveal subsurface features or structural irregularities beneath the surface. On a more speculative note, if the object exhibits behaviors such as deliberate maneuvering or variable brightness that are independent of the solar illumination angle, these would be highly significant. Normally, brightness fluctuations follow the pattern of sunlight, getting brighter as the object faces the sun and dimmer as it turns away. If instead the brightness varies for reasons unrelated to sunlight, this could suggest active control or internal processes that defy straightforward natural explanation. There has also been some discussion about whether NASA's Mars Reconnaissance Orbiter might attempt to image the object with its high-rise camera, which boasts incredibly high resolution for planetary science. However, it's important to approach this possibility with caution. As of now, there is no official confirmation that the high-resolution imaging science experiment, HiRISE, will be tasked with this observation during the flyby. While it remains a plausible scenario given the scientific value of such data, we must treat it as a watch this space situation, pending any formal announcement from NASA or the mission teams. Looking ahead, another key player in observing this interstellar visitor is the European Space Agency's JUICE mission. Launched in 2023 and currently en route to Jupiter's icy moons, JUICE is in a position that could later allow it to contribute valuable observations. As the trajectory of the object takes it farther into its path, JUICE might provide a long baseline perspective from a different vantage point within the solar system. Such multi-point observations, spread over weeks or months, are essential for accurately determining the orbit and detecting any subtle changes in behavior or trajectory. They help us piece together a more complete picture and are especially useful for testing hypotheses about the object's origin, composition, and potential artificial features. However, it's important to temper expectations. The immediate data from tonight's flyby and upcoming perihelion passage might not yield definitive answers right away. The full analysis pipeline involves data transmission, calibration, noise reduction, and detailed modeling, processes that often take days, weeks, or even months before results are publicly available. Nonetheless, the integration of observations from different instruments and missions along with ongoing analysis forms the foundation for understanding this mysterious visitor. In the coming days or even weeks, the first publicly released images or spectral data from tonight's close pass of 3I Atlas may not immediately become available. This is simply due to the complex multi-stage process that transforms raw data into meaningful scientific information, a pipeline that involves meticulous calibration, processing, analysis, and validation. Initially, the data transmitted from the spacecraft arrives as an unrefined stream of photons and signals. These raw signals contain various artifacts, cosmic ray hits, instrumental noise, calibration drifts, and other systematic distortions. The first step involves applying calibration procedures which correct for these artifacts, subtract backgrounds, and convert the raw signals into standardized, physically interpretable units such as brightness and spectral flux. Once calibrated, the data undergoes further processing to enhance the signal-to-noise ratio, allowing scientists to distinguish genuine features from background noise. This step often involves sophisticated algorithms and modeling techniques, aiming to clarify the subtle details hidden within the measurements. Following this, the science teams write detailed reports or papers, carefully analyzing the data, comparing it with theoretical models, and validating the results internally, often through peer review or rigorous internal scrutiny, before any public dissemination. Only after this thorough vetting does the data typically get published, either in peer-reviewed journals as preprints shared among the scientific community, or through official press releases. This gradual, deliberate process is the standard in scientific practice, designed to ensure accuracy and reliability. It's important to understand that the delay is not due to any sinister intent or cover-up, but reflects the careful, methodical nature of scientific investigation. So if you're expecting an immediate announcement tomorrow morning claiming definitive evidence, either confirming or dismissing the nature of 3I Atlas, such hope should be tempered. The eventual goal, however, remains clear: to produce a much sharper, more detailed picture of what this intriguing object is doing at this critical juncture in its journey past Mars. This refined understanding will then inform the next fundamental question: what is the true composition of 3I Atlas? This leads us into the third part of our exploration, the anatomy of 3I Atlas. Let's delve into what we currently understand about the physical makeup of this object, though I must warn you up front that the knowledge is limited and somewhat uncertain. The most frustrating aspect is the broad range of size estimates. The Hubble Space Telescope's observations have placed an upper limit on the nucleus's size at roughly 5.6 kilometers across. However, the presence of an extremely active and luminous coma complicates the matter. The bright cloud of gas and dust surrounding the nucleus obscures direct measurement, meaning the actual size of the core could be significantly smaller. Some scientists have estimated the nucleus's size to be as small as 320 to 440 meters, about a tenth of the upper limit, leading to a volume uncertainty spanning 3 orders of magnitude. To put this into perspective, if this were a criminal investigation, we'd be describing the suspect as anywhere between 5'2" and 6'8". Hardly a precise identification. The root of this uncertainty is straightforward. We are not observing the nucleus directly. Instead, we're seeing sunlight scattered off the particles in the surrounding coma, which acts like a glowing fog, concealing the object's true dimensions. It's akin to trying to see a tiny pebble at the bottom of a turbulent, muddy river. You know it's there because physics dictates its existence, but direct measurement remains elusive. Adding to the intrigue, recent detailed analyses of the object's trajectory, derived from observations made by a network of observatories worldwide, including both amateur and professional facilities, have achieved remarkable precision. By tracking the object over several months and fitting its orbit to the accumulated data, scientists can detect minute deviations from a purely gravitational trajectory. These deviations, known as non-gravitational accelerations, are caused by the outgassing of gases from the nucleus as it warms near the Sun. For 3I Atlas, the non-gravitational acceleration has been measured to be approximately 3 times 10 to the negative 10th astronomical units per day squared, a truly tiny force. Interestingly, many active comets exhibit accelerations many orders of magnitude larger, owing to vigorous outgassing. Yet, in the case of 3I Atlas, the observed acceleration is extraordinarily weak, despite clear signs of outgassing. By combining this tiny acceleration measurement with the rate of outgassing observed by JWST, scientists can perform a back-of-the-envelope calculation to estimate the minimum mass of the object. The results suggest that the object must weigh at least 33 billion metric tons. Assuming a typical cometary density, around 500 kilograms per cubic meter, this mass corresponds to a nucleus of at least 5 kilometers in diameter. In summary, despite the significant uncertainties, current data collectively point towards a substantial, roughly 5-kilometer-wide object that is actively outgassing, with a mass so great that its gravitational influence on its outgassing gases is minimal. This combination of factors makes the physical nature of 3I Atlas a fascinating puzzle. Blending observational notice, anything? That observation alone immediately highlights just how intriguing this object truly is. Its estimated size, as derived from Hubble's measurements, hovers at the upper limit of the constraints we've established, around 5.5 kilometers across. This suggests that the object is either genuinely large and hefty, or perhaps our assumptions underlying the mass estimation are flawed. Maybe the outgassing process isn't as symmetrical as our models predict. Alternatively, there could be something about its internal composition or surface structure that makes its acceleration less efficient than expected. Perhaps uneven distribution of volatile materials or a peculiar internal architecture. Or, and here's the unsettling thought, maybe it's not a comet at all. Let's delve into the chemistry because that is precisely where 3I Atlas stands out in a startling way. The James Webb Space Telescope's near-infrared spectrograph, or NIR spec, observed the coma of this object on August 6, 2025, and the results are compelling. It revealed a carbon dioxide to water ratio of approximately 8:1. To put this into perspective, most comets within our solar system, especially those observed at similar distances from the Sun, show water as the dominant volatile component, often by a significant margin. Typically, the ratio might be closer to 1 part carbon dioxide to 20 parts water, or even more water-rich. But 3I Atlas has completely reversed that expectation. Instead of water reigning supreme, it's producing 8 times more carbon dioxide than water, an anomaly that's hard to ignore. Alongside these two volatiles, the spectroscopic analysis also detected traces of carbon monoxide, carbonyl sulfide, and water ice grains, the entire chemical cocktail you might expect from a comet. Yet the proportions are nothing short of bizarre. So what could explain such an unusual chemical signature? One plausible explanation relates to the object's formation environment. In a protoplanetary disk, the swirling cloud of gas and dust from which planets and small bodies coalesce, the temperature decreases as you move farther from the central star. Different ices condense out at specific distances, a process known as the snow line or frost line. Water ice tends to form relatively closer in, where temperatures are warmer, while carbon dioxide and carbon monoxide ices solidify further out, in colder regions. If 3I Atlas originated near what astronomers call the CO2 ice line in its original system, it might naturally be enriched in carbon dioxide relative to water. That's an elegant natural explanation grounded in current astrophysical understanding. Alternatively, radiation processing offers another compelling possibility. Imagine this object has been drifting silently through interstellar space for millions of years, continuously bombarded by cosmic rays and ultraviolet radiation from distant stars. This intense radiation can break molecular bonds on the surface, transforming and creating new chemical compounds, effectively altering its original composition. Furthermore, radiation can produce an insulating crust, a layer of processed refractory material that traps more volatile substances beneath the surface. If this crust preferentially seals in water ice but allows carbon dioxide to escape more readily, it would result in the skewed outgassing ratios we observe. In essence, the object's surface chemistry has been radically altered by its long interstellar journey, making it an exotic, natural anomaly. Turning to the trajectory, the object's path is unequivocally hyperbolic, meaning it is moving faster than the escape velocity of our solar system. This is a critical signature. It indicates the object came from outside the gravitational bounds of the Sun, passing through on a one-time hyperbolic orbit. There's no bound orbit, no looping around the Sun. Instead, it is swinging past at high velocity before heading back into the dark, interstellar abyss. Its perihelion, its closest approach to the Sun, is expected around October the 30th, 2025, at about 1.4 astronomical units from the Sun. That's just outside Earth's orbit, closer than Mars but farther than Venus. At this perihelion, solar heating will reach its maximum. If there are any dramatic changes or peculiar behaviors, such as sudden outbursts or unexpected activity, they are most likely to manifest during this window. It's worth emphasizing the sheer speed at which this object is passing. Approximately 210,000 kilometers per hour, or about 130,000 miles per hour, roughly 58 kilometers per second. That's more than 30 times faster than the Voyager 1 spacecraft, which is currently the fastest human-made object leaving our solar system. This incredible velocity underscores the object's interstellar origin and its high-energy passage through our planetary neighborhood. Currently, Voyager Odin holds the distinction as the fastest human-made object venturing beyond the confines of our solar system, hurtling away at approximately 17 kilometers per second relative to the Sun. In stark contrast, the interstellar visitor known as 3I Atlas surpasses that velocity by more than 3 times, reaching extraordinary speeds that leave our spacecraft in the dust. This immense velocity results from a combination of its initial drift through interstellar space, once set in motion eons ago, and the gravitational pull exerted by the Sun as it journeys inward. Together, these factors accelerate 3I Atlas to a speed that definitively confirms it did not originate within our solar system, establishing beyond any reasonable doubt that it hails from somewhere beyond the stars. To better understand this, let's compare such velocity with typical comet behavior in our cosmic neighborhood. Most comets in our solar system, even the long-period ones originating from the distant Oort cloud, tend to show a water-dominant volatile profile when active. Normally, as they venture closer to the Sun, the ratio of carbon dioxide to water changes only at very large distances, where the Sun's warmth is insufficient to cause water ice to sublimate efficiently. But more volatile substances like carbon dioxide can still escape. In those frigid outer reaches, CO2 outgassing can outpace water, creating a higher ratio. However, 3I Atlas defies this pattern by remaining active relatively close to the Sun, maintaining an unusual chemical ratio that stands roughly 6 standard deviations above what we expect based on solar system comets. An outlier so extreme that in statistical terms it prompts serious questions about whether it even belongs to the same population. Adding to the mystery, we encounter the so-called acceleration paradox. Normally, when a comet outgasses, the gases act like tiny thrusters, exerting a force that nudges the body and causes measurable acceleration. Yet, observations from the James Webb Space Telescope reveal abundant outgassing activity, while the actual push on 3I Atlas remains astonishingly minimal. How can this be? One plausible explanation involves the concept of balanced jets. If the nucleus vents material from multiple locations, with jets oriented in such a way that their forces cancel each other out, the object can appear highly active, gas flowing from various spots, yet exhibit little to no net acceleration. Picture 4 rocket thrusters firing simultaneously in a square pattern, each with equal strength but directed in opposite directions. The body would tremble from the activity but remain stationary. This scenario is not only plausible but also common among some known comets, which display complex jetting patterns. However, it requires a specific symmetrical geometry that has yet to be confirmed in the case of 3I Atlas. Alternatively, the minimal acceleration could suggest that the object is simply extraordinarily massive. Think of trying to move a boulder with a leaf blower. There's a lot of air moving, but the effect on the heavy object is negligible. If 3I Atlas is truly a solid body stretching 5 kilometers across with a dense, sturdy interior, then the gases produced during outgassing might simply be insufficient to produce a significant push. Mathematically, this explanation fits the observations, but it also implies that we are dealing with a cosmic behemoth. The idea of discovering such a large interstellar object so early in our survey. History strikes many as statistically improbable. Yet here we are, confronting that very possibility. So what does this mean in terms of its physical structure? Based on current data, the object's size likely falls somewhere between 300 meters and about 5.6 kilometers across. It is enveloped by an active asymmetric coma, an atmospheric cloud of gas and dust, rich in carbon dioxide. Its trajectory unmistakably indicates an interstellar origin, moving at an astonishingly high velocity that leaves no doubt about its extraterrestrial passage. The chemistry of its outgassing is off the charts, defying the typical ratios observed in our solar system's comets. Despite all this exuberant activity, the object is surprisingly resistant to being pushed around. Its jets, though vigorous, exert minimal force, hinting at an extraordinary combination of size, mass, and perhaps even structural composition. Every measurement we gather seems to deepen the enigma, layering new complexities rather than bringing clarity to the overall picture. This persistent strangeness is precisely what prompts some to question whether we're even scrutinizing the right object altogether. Perhaps instead of trying to understand a natural celestial visitor, we should consider the possibility that we're observing something fundamentally artificial. This brings us to the core of Part 4, the Loeb scale and the Shestasat percent verdict. Let's confront the proverbial elephant lurking within the telescope's field of view. Avi Loeb, a prominent figure in astrophysics, chair of Harvard's astronomy department and former chair of the board on physics and astronomy at the National Academies, has developed a systematic framework designed to quantify just how likely an interstellar object might be artificial in origin. He calls this the Loeb scale, a numerical rating system that ranges from 0 to 10. At the lower end, 0 signifies complete certainty of natural origin, an ordinary rock or comet with absolutely no suggestion of technological intervention. Conversely, a 10 indicates definitive proof of extraterrestrial technology, possibly even dangerous in intent or design. The scale is intentionally modeled after existing evaluative tools used for other existential risks, such as the Torino scale, which assesses asteroid impact threats, or the Richter scale, which measures earthquake magnitudes. The goal is to provide a universal language that helps researchers, media outlets, and the public discuss objects that have, until now, often been dismissed outright or sensationalized beyond reason. In the early days of August in the year 2025, some public commentary, driven by the accumulating data, assigned a provisional rating of 6 out of 10 to 3I Atlas within this framework. That rating, representing a 60% confidence level, suggests a significant suspicion that the object could be of technological origin. Notably, this was based on preliminary assessments and the limited data available at that time. As more information poured in, particularly the spectral chemistry results obtained from the James Webb Space Telescope, Loeb revised this estimate downward, reflecting increased caution. His updated rating was 4 out of 10, or 40%. This indicates a still elevated, though less confident suspicion that the object might not be merely a natural space rock. It admits the possibility that something more complex could be at play. Such a revision exemplifies the dynamic nature of scientific evaluation, where initial hypotheses are constantly refined in light of new evidence. This ongoing debate has profoundly divided the astronomical community. Some members remain cautious, leaning toward natural explanations, while others entertain the possibility of artificiality with increased seriousness. The central question remains: what factors could cause the Loeb score to rise? Let's explore Loeb's reasoning, which, regardless of personal agreement, follows a logical and methodical approach. First, consider the size of 3I Atlas. If it is truly 5 kilometers or larger, something suggested by the dynamical models and mass estimates, that's an extraordinary rarity. The vast majority of objects drifting through interstellar space are believed to be smaller because smaller bodies are exponentially more common in planetary debris populations. Detecting a sizable object, comparable in scale to the asteroid that caused the dinosaurs' extinction so early in our survey history when only 2 other interstellar visitors are confirmed, appears statistically improbable. It's akin to winning the lottery on your 3rd ticket. Possible, yes, but highly suspicious from a probabilistic standpoint. Next, examine the observed non-gravitational acceleration, or rather its surprising weakness. If the object is actively outgassing enough material to produce a visible coma detectable by JWST spectra, we would expect it to be influenced by the recoil from that outgassing, causing a measurable push or drift. The fact that the push remains minimal despite evident activity suggests either that the object is exceptionally massive, resisting acceleration, or that its thrust profile is somehow perfectly balanced, canceling out net movement. Loeb notes that both scenarios are plausible natural phenomena. However, they are also consistent with the hypothesis that the object could be a large, solid artifact venting something for reasons unrelated to typical thermal sublimation processes. Third, the chemistry presents a compelling anomaly, an 8-to-1 ratio of carbon dioxide to water. This ratio is remarkably unusual. Most comets observed within our solar system tend to be water-rich, with water ice being the dominant volatile component. An 8-fold excess of CO2 compared to H2O defies the typical pattern seen in the natural comet population. Such a composition is genuinely odd, prompting questions about its formation environment or subsequent processing history. Topics we will explore further. Together, these factors, size, outgassing behavior, and chemistry, compose a complex puzzle. Loeb's framework aims to quantify the probability that the object we observe is of artificial origin, providing a systematic way to track how our confidence level evolves as data accumulates. While these assessments are inherently probabilistic and subject to revision, they serve as valuable tools for guiding scientific inquiry and public understanding amid uncertainty. In sum, the Loeb scale and the associated Chess-Desat. While it's true that the data and chemistry observed so far align with natural explanations, it's worth considering a hypothetical scenario. If one were designing an interstellar probe, the choice of propellant might be driven more by considerations of efficiency and long-term storage than by cosmic abundance. For instance, carbon dioxide sublimates at higher temperatures than water ice, making it potentially more manageable for storage over millions of years in the cold vacuum of space. This is, of course, speculative, an educated guess rooted in engineering logic rather than concrete evidence. But it's precisely the kind of subtle detail that can make even the most rational scientists' antennas twitch with curiosity and suspicion. However, what truly pulls the scientific score down, at least for now, is the composition of the coma itself. The James Webb Space Telescope's spectral analysis reveals clear signatures of common natural volatiles: water, carbon dioxide, carbon monoxide, carbonyl sulfide, and water ice grains. These are exactly the sorts of molecules and dust particles one would expect from a typical comet heated by the sun's radiation. Nothing particularly exotic or artificial here. There's no indication of industrial compounds, no unusual isotopic ratios that might hint at artificial synthesis, and no narrowband emissions that could be interpreted as leakage from electronics or other technology. The outgassing appears consistent with a natural process of sublimation driven by solar heating, aligning perfectly with the behavior of known comets. This robust evidence provides a strong case for the natural origin hypothesis, reinforcing the idea that we are observing a regular, if somewhat unusual, cosmic visitor rather than something engineered. The absence of any visible maneuvers further complicates the artificial hypothesis. If 3I Atlas were a functioning spacecraft or probe, one would expect to see deliberate course corrections, accelerations or decelerations that deviate from what simple gravitational forces and outgassing would produce. Instead, its trajectory so far remains entirely ballistic, in line with orbital mechanics influenced only by gravity and minimal outgassing effects. There's no sign of active control systems or thrusters adjusting its path, which would be a hallmark of an artificial craft seeking to achieve specific observational or navigational goals. Another point favoring the natural explanation is the geometry of its arrival. Some speculative minds have suggested that if an alien probe aimed to study our solar system covertly, it might approach from an unusual angle to avoid detection or to maximize data collection. But the orbit of 3I Atlas isn't particularly suspicious. It's inclined, but that's entirely consistent with what we expect from interstellar objects. These bodies are not formed within our solar system and therefore do not follow the ecliptic plane. Its approach appears to be at a typical, somewhat random angle, not deliberately stealthy or optimized for observation. It simply doesn't scream intentional survey or stealth approach, but rather mimics the pattern of natural interstellar visitors. Mainstream astronomy agencies, including NASA and the European Space Agency, maintain a cautious stance. Official statements describe 3I Atlas as an interstellar comet, nothing more threatening than a natural object passing through our neighborhood. Their language is measured and careful, emphasizing that current data does not suggest any danger to Earth and that, unless something radically unexpected occurs, the object remains a natural entity. Most professional astronomers commenting publicly are in the comet camp, pointing out that despite its unusual chemistry, unusual does not equate to impossible. Our current sample size of interstellar objects is only 3, Comet Borisov, Oumuamua, and now 3I Atlas. And drawing sweeping conclusions based on such a small data set is akin to trying to determine the average height of humans by measuring just 3 individuals. You might get a rough sense, but it's unlikely to be accurate. Yet, amidst this cautious consensus, the media landscape muddles the picture. Some outlets, especially those eager for clicks and sensational headlines, amplify the alien narrative. Headlines scream about motherships, invasion fleets, or alien probes passing by Mars. Conversely, others ridicule or dismiss these notions outright, branding anyone entertained by the possibility as conspiracy theorists or attention seekers. This polarizing coverage creates a confusing, often misleading narrative that complicates public understanding and the scientific process alike. In the ongoing dialogue about objects like 3I Atlas, the most balanced scientific perspective, one that accepts the possibility of natural origins while remaining vigilant, often finds itself marginalized, drowned out by the louder currents of sensationalism and engagement-driven narratives. Nuanced thinking, although essential for scientific integrity, tends to be overshadowed by the appetite for headlines, clicks, and viral stories. This creates a paradox, the core principle of fairness in science, namely that extraordinary claims demand extraordinary evidence, becomes harder to uphold in public discourse where simplicity and spectacle prevail. The phrase, "extraordinary claims require extraordinary evidence," popularized by the eminent scientist Carl Sagan, has become almost a guiding mantra in scientific integrity. It underscores a fundamental rule. If one asserts that an object like 3I Atlas is an alien spacecraft, the evidence needed to support such a claim must be unequivocal and compelling. What would that evidence look like? It would have to include unmistakable signals or features, things that leave no room for natural explanations. For instance, engine-like maneuvers that cannot be attributed to outgassing or gravitational influences, narrow-band radio emissions at frequencies that do not occur naturally, optical signatures that clearly indicate manufactured surfaces, such as specular reflections, panel-like glints, or geometric structures that defy the randomness expected from natural bodies, or thermal emissions that deviate from what solar heating would produce, suggesting some form of internal power or technological activity. Essentially, to move from the realm of the plausible to the probable, the evidence must unambiguously scream technology, leaving no doubt about artificial origin. Recognizing the difficulty of such conclusive evidence, Loeb's framework endeavors to formalize this burden of proof into a quantifiable scale. Rather than a simple binary, natural or artificial, the scale is designed to be fluid, a sliding continuum that adjusts as new data becomes available. Initially, with limited observations, an object might be assigned a higher probability of being artificial because of the inherent uncertainty. Over time, as additional measurements, such as spectral data, trajectory analysis, or surface imaging, align more closely with natural models, the probability decreases. This iterative process embodies the scientific method. Hypotheses evolve in response to accumulating evidence. Take 3I Atlas as an example. Its initial assessment, a 6 out of 10 on the artifact likelihood scale, was rooted in the scant data available at first. As observations from the James Webb Space Telescope and other instruments have refined our understanding, showing a chemistry dominated by carbon dioxide with no observed maneuvers, this score has been revised downward to 4 out of 10. The reduction reflects increased confidence in a natural, comet-like explanation, though it leaves room for continued uncertainty. Should subsequent observations reveal that the object behaves in a predictable, stable manner throughout perihelion, the score could decrease even further, reinforcing the natural origin hypothesis. However, the scale also introduces a second dimension, threat versus benign, that adds philosophical depth to the discussion. An object's likelihood of being artificial does not necessarily correlate with its danger. For example, an artificial artifact could be a benign, long-dead probe, or a dormant, non-threatening relic from a civilization that long ago faded into silence. Conversely, a natural object, such as a comet on a collision course, could represent a significant threat, regardless of its origin. These two axes, artifact probability and threat level, are independent. A high probability of being an alien probe does not automatically equate to imminent danger, just as a threatening natural object does not imply extraterrestrial origin. The Loeb scale thus functions as a hypothesis-generating tool, akin to a Bayesian prior. It begins with an initial probability based on current evidence and updates dynamically as new data emerges. Most experts would presently assign a low prior probability, perhaps a fraction of a percent, to the hypothesis that 3I Atlas is an alien craft, given the current body of evidence. Yet the very existence of a formal systematic scale encourages a more disciplined approach to evaluation, avoiding the pitfalls of overhyping or dismissing possibilities prematurely. Looking ahead, the upcoming capabilities of the Vera Rubin Observatory, soon to be operational, promise to revolutionize our detection and classification of interstellar visitors. Its unprecedented sensitivity and wide-field surveys will identify objects at a rate orders of magnitude higher than current methods. This proliferation of discoveries will necessitate a common language, like the Loeb scale, to categorize and interpret these objects efficiently. Such a framework ensures that scientific discourse remains structured, transparent, and adaptable, providing a robust tool for navigating the complexities of potential interstellar phenomena. Certainly. Here's a deep, polished, and expanded paraphrase of your provided excerpt, emphasizing clarity, flow, and the underlying scientific reasoning. So what's the true likelihood that 3I Atlas is an artifact of alien technology? Based on current evidence, the most reasonable estimate is that it's almost certainly not. The probability that it's a manufactured object, an alien probe or craft, stands at a very low margin, perhaps less than 1 in 2, but that doesn't mean it's impossible. It's roughly a 40% chance, still not high, but enough to keep the question open and worthy of serious consideration. The key point is this: the probability isn't zero, and that's precisely what Avi Low and other researchers are urging us to confront. Whether you see that question as provocative or simply pointless, it's the one that sustains this story's momentum. As instruments orbiting throughout the solar system turn their sensors toward that tiny, faint speck hurtling past Mars tonight, it's that lingering uncertainty that keeps the investigation alive. Next, we need to delve into the fundamental physics that confirm this object's interstellar origin. Understanding where the mathematical lines begin to crack is crucial. This is part 5 of our exploration, the physics puzzle. How do we actually establish that 3I Atlas isn't just another comet or asteroid from our solar neighborhood, but genuinely comes from beyond the bounds of our star system? That's far from a trivial question. The universe is vast, really vast, and objects move through it in complex, often unpredictable ways, heavily influenced by multiple gravitational fields. You can't simply look at an object zipping through space and declare with certainty that it's an alien probe or a fragment from another star. You need rigorous orbital mechanics, the precise application of celestial physics, to determine the origin of such a body. Fortunately, we have the tools. When astronomers track an object across the sky over the course of weeks or months, each observation provides a coordinate, its right ascension and declination at a specific moment in time. By gathering enough of these data points, scientists input the measurements into specialized orbital mechanics software. These programs then solve for the 6 parameters that define an orbit: the semi-major axis, eccentricity, inclination, argument of perihelion, longitude of the ascending node, and the time of perihelion passage. For objects gravitationally bound to the Sun, like planets, asteroids, and comets, the orbit is an ellipse, and the eccentricity is less than 1. Such an orbit is closed, repeating periodically over multiple revolutions. But for bodies originating outside our solar system, interstellar objects, the rules are different. Their orbits are hyperbolic, meaning the eccentricity exceeds 1. These trajectories are open-ended, and the object does not orbit the Sun in a closed loop. Instead, it is passing through, coming from infinity, swinging around the Sun and then continuing outward, never to return. In the case of 3I Atlas, the data clearly indicates an eccentricity significantly greater than 1. This hyperbolic orbit is a key signature. There's no closed solution, no bound orbit, implying that the object is not gravitationally tethered to our star. It's a visitor from elsewhere in the galaxy. Another critical indicator is the hyperbolic excess velocity, the speed that the object has relative to the Sun once you subtract the influence of solar gravity. For 3I Atlas, this excess velocity is on the order of tens of kilometers per second, roughly the speed it was already traveling through interstellar space before it encountered our solar system. Such a velocity is well beyond what natural processes within our star system can produce without significant assistance. Within our solar neighborhood, there are no known mechanisms, no gravitational slingshots or interactions, that could impart such a high velocity to a passive object without a close encounter with a massive planetary body. The trajectory of 3I Atlas doesn't pass near any such body in a manner that could explain its current speed. This suggests that the object arrived here with that velocity, rather than gaining it through gravitational acceleration inside the solar system. However, this is where the uncertainties begin to creep in. While we can measure the current orbit with exceptional precision, pinpointing its position and velocity as it whizzes past, the key challenge is reconstructing its past trajectory. We can project the orbit backward in time, estimating where it might have come from. But roughly is the operative word. The further back we go, the more the tiny errors in measurement compound. Small uncertainties in the current position and velocity snowball over millions of years, transforming into enormous margins of error when retracing the object's origin. In practical terms, this means we can confidently say that 3I Atlas originated somewhere outside our solar system, probably from a direction consistent with its current trajectory. But pinpointing the exact star system or even the precise region of the galaxy it came from remains beyond our reach at this point. The best we can. Certainly. Here's a deep, richly expanded and polished version of the passage, maintaining all factual details while enhancing clarity and flow. The complexity of the galactic velocity field makes precise tracing of an interstellar object's origin an immensely challenging task. Stars do not simply passively drift in a static universe. They move, sometimes quite rapidly, and their gravitational influence can perturb nearby objects. When astronomers attempt to backtrack the orbit of such an object over vast stretches of cosmic time, say, 1,000,000 years, the uncertainties balloon dramatically. The orbital path, once mapped backward, can spread out over dozens of light years, making pinpointing its exact origin akin to trying to find a single grain of sand in a sprawling desert. Stretch that timeline to 10 million years, and the uncertainty widens even further to hundreds of light years. In essence, the original trajectory becomes a broad, indistinct corridor rather than a pinpoint line, making precise source identification nearly impossible. Beyond orbital uncertainties, a crucial question persists. What mechanism could have ejected such a sizable object from its parent star system in the first place? Stars do not randomly toss large, multi-kilometer bodies into interstellar space without cause. Instead, these objects are typically expelled through dynamic and energetic processes during planetary system evolution. One of the primary mechanisms involves gravitational scattering by massive planets during the tumultuous early phases of a star's life. In young star systems, chaotic, turbulent environments, planets often migrate chaotically, changing their orbits in response to interactions with planetesimals, gas, and other bodies. During this chaos, asteroids and comets can be flung outward with enough velocity to escape the star's gravitational grip, becoming rogue interstellar travelers. Computational models of planetary formation and evolution support this idea, showing that a significant fraction of primordial material, ranging from small bodies to large fragments, can achieve escape velocity in such chaotic systems. In fact, some estimates suggest that there may currently be trillions of rogue comets and asteroids drifting through our galaxy, outnumbering the stars themselves. These free-floating objects are not bound to any star, wandering aimlessly in the interstellar medium, their numbers vast enough to make their presence statistically inevitable. Another plausible origin involves close encounters between stars. When two stars pass within a few light years of each other, an event not uncommon over galactic timescales, the gravitational forces at play can dramatically influence the structures around each star. Tidal forces can strip comets from their respective Oort clouds, sending these icy bodies hurtling outward into interstellar space. Such stellar flybys act as cosmic slingshots, flinging material into the void. In more dramatic scenarios, a star might be ejected from a densely packed star cluster, carrying with it some of its cometary and planetary debris. Once expelled, this material becomes part of the galactic debris field, drifting through space for eons. Alternatively, and perhaps most catastrophically, a planetary collision or tidal disruption event could produce a burst of debris. Imagine a planet wandering too close to its parent star and being ripped apart by tidal forces, an event called tidal disruption. The resulting fragments, ranging from dust-sized particles to kilometer-sized chunks, are hurled outward at high velocities, dispersing into interstellar space. Similarly, a supernova explosion, an immensely energetic stellar death, can send shockwaves through nearby systems, shattering planets and ejecting fragments at tremendous speeds. These violent processes can create streams of debris, fragments that span a broad-sized spectrum and that can survive in the cold, dark depths of interstellar space for millions or even billions of years. Looking ahead, an important upcoming event is the perihelion passage of the interstellar object known as 3I Atlas. Scheduled for just under a month from now, on October 30th, 2025. At that point, the object will reach its closest approach to the Sun, coming within approximately 1.4 astronomical units, roughly the distance from the Sun to Mars. Solar heating will be at its peak, and natural expectations suggest that if 3I Atlas is a typical comet, we should observe a marked increase in outgassing activity. The sublimation rate, the process where ice turns directly into gas, should spike, causing the coma, the cloud of gas and dust surrounding the nucleus, to brighten significantly and possibly expand as more material is released. If, during this perihelion, the measured non-gravitational acceleration, the tiny push resulting from the outgassing, remains low or does not increase proportionally with the expected rise in activity, it would lend support to the heavy nucleus hypothesis. This model proposes that the object is intrinsically massive, perhaps a solid, dense body with enough mass that the gases released are insufficient to produce a noticeable change in its path. While the outgassing might appear dramatic to our instruments, it would still be inadequate to significantly alter the trajectory, implying a large, dense core. However, perihelion could also reveal I am not asserting that we will find direct evidence of maneuvering by this object. Rather, I emphasize the importance of conclusively ruling out the possibility with high confidence. The mass estimate derived from JWST's mass loss measurements, coupled with the orbital dynamics, suggests a minimum mass of approximately 33 billion tons. However, it's crucial to acknowledge the assumptions embedded within this figure. This estimate presumes that the outgassing rate JWST observed in early August accurately reflects the object's typical behavior over the entire period used for orbit determination. If in reality the object exhibits variability, being more active at certain times and less active at others, the inferred mass would consequently fluctuate. Furthermore, the calculation assumes that the outgassing is either roughly symmetrical, or, at the very least, that any asymmetries average out over the object's rotation. Should there be a persistent jet or active region exerting a steady push in a specific direction, the simple mathematical model would need adjustment. It also relies on an assumed efficiency in how outgassing translates into thrust, a parameter heavily dependent on the molecular weight of the gases involved and the velocity at which they are expelled. Since molecules like carbon dioxide and water vapor differ in molecular weight, their relative proportions, the mix, play a significant role in the thrust calculation. Therefore, the figure of 33 billion tons should be viewed as a lower bound, grounded in particular modeling assumptions rather than an exact measurement. This estimate is not comparable to the size constraints provided by the Hubble Space Telescope, which directly measures the physical dimensions of an object. Instead, it remains an inference, an educated estimation derived from models, whose accuracy hinges on the validity of the underlying assumptions. In the case of the size and shape, for example, we would need to measure the rotation rate and the periodic brightness variations to gain substantial insights into the object's geometry. A perfectly spherical object rotating uniformly would not produce noticeable brightness fluctuations. Conversely, an elongated or irregularly shaped object tumbling end over end would cause its brightness to wax and wane as different cross-sections face our line of sight. The amplitude of these brightness variations can inform us about the axis ratio, the ratio of length to width of the object, while the period of fluctuation reveals its spin rate. However, capturing this data requires high-cadence photometric observations over extended intervals. which is complicated by the presence of the surrounding coma. The coma's brightness often dominates the observed signal, making it exceedingly challenging to isolate the true rotational light curve of the nucleus itself. Disentangling the nucleus's rotation from the coma noise demands precise, continuous observations, which may become feasible with future measurements, such as an occultation event where the object passes in front of a background star, providing a direct size estimate. Alternatively, radar observations, though difficult at such distances, could potentially yield size and spin information if successfully conducted. If the object's activity diminishes significantly after perihelion, allowing us to observe the nucleus directly with instruments like the Hubble or JWST, we could finally determine its dimensions with greater certainty. A notable historical parallel is the first interstellar visitor, Oumuamua, which spurred numerous papers attempting to trace its origin. Researchers used data from Gaia, the star mapping mission, to identify candidate star systems that might have ejected it. Despite these efforts, the uncertainties remain substantial because over millions of years, tiny perturbations from passing stars, radiation pressure, and interstellar dust forces accumulate, complicating efforts to pinpoint its precise origin. The same fundamental problem applies to Oumuamua's successor, Oumuamua-2, or in this case, 3I Atlas. Its trajectory, like that of Oumuamua, has been influenced by a multitude of minor forces and gravitational interactions over vast timescales, making backtracking to its source a challenge. The uncertainties grow larger as we trace the object's journey further into the past, emphasizing the difficulty in definitively establishing its origin or precise physical properties based solely on current orbital data. We can confidently state that this object originated from beyond our solar system, traveling through interstellar space in a general direction consistent with such an origin. However, we cannot precisely trace it back to any specific system such as Tau Ceti, nor can we confirm whether it was ejected from the Hyades cluster. The resolution of our current observations simply isn't sufficient to pinpoint its exact source or origin point. A crucial concept to understand here is the jet cancellation mechanism, an explanation that deserves a straightforward, accessible analogy because it plays a central role in reconciling the apparent contradiction between the object's weak acceleration and its vigorous outgassing. Imagine a comet nucleus shaped somewhat like a potato, with multiple active patches on its surface emitting gas, outgassing in different regions. If these patches are distributed symmetrically and each produces roughly the same thrust, then the forces they generate can effectively cancel each other out. Think of it as four people pushing a car from four sides with equal strength. No matter how hard they push, the car doesn't move. Instead, the car just experiences stress and strain. This is a form of exotic physics, one we've observed in our own solar system. For example, the comet 67P Churyumov-Gerasimenko, which the Rosetta spacecraft orbited for nearly 2 years, exhibited this very behavior. It had multiple active regions emitting jets in complex patterns, yet its overall non-gravitational acceleration remained modest because the jet's forces mostly balanced each other out, resulting in little net push. This balanced jet scenario is plausible for 3I Atlas, but it does require a specific geometric arrangement of the active regions and their jets. Not all comets exhibit this behavior. Some are dominated by a single large jet, which results in a much stronger acceleration. The fact that 3I Atlas appears to fall into the balanced jets category is another piece of evidence consistent with natural processes, albeit a somewhat unusual one. There's also a valuable community-driven scientific aspect to this discussion that's worth highlighting. The orbital calculations for 3I Atlas are based on thousands of precise position measurements gathered from observatories around the world. Professional facilities like Gemini, Subaru, and the European Southern Observatory. as well as countless amateur astronomers with backyard telescopes, all contributing data to the Minor Planet Center. This large-scale citizen science effort provides a collective, distributed network of observations, each one refining the orbit, tightening the uncertainties, and helping us develop better models. Without this extensive network of observers, our understanding of what this object is doing would be far less clear and much more uncertain. So where does all this lead us? The case for 3I Atlas being a natural, albeit strange object is quite strong. Its chemistry, though unusual, remains explainable within natural frameworks. Its size and mass estimates are uncertain but not impossible. Its trajectory is undeniably interstellar. The puzzling aspect, the weak acceleration despite apparent strong outgassing, can be explained through the balanced jets mechanism, or the possibility that it's a high-mass object. Every individual anomaly has a plausible natural explanation. However, these anomalies continue to accumulate, and their combined effect creates a sense of strangeness that's hard to ignore. It's akin to a murder investigation where each piece of evidence could have an innocent explanation. Yet when all pieces are laid out together, a suspicious pattern emerges. The door isn't fully closed. It's cracked open with light spilling through the gap. Our next step is to compare three primary hypotheses directly and determine which one best withstands the ongoing scrutiny of incoming data. The first, the comet hypothesis, nature's exotic but familiar child. Let's begin with that most straightforward explanation. The simplest explanation, one that requires the fewest assumptions and aligns most seamlessly with our existing understanding of the universe, is that 3I Atlas is a comet. More specifically, an interstellar comet. Yes, it is an unusual comet with chemistry that is certainly exotic by our solar system standards, but fundamentally it remains a dirty snowball, a fragment of ice and rock that originated in the protoplanetary disk surrounding another star. This icy body was ejected through gravitational interactions during the tumultuous early days of planetary formation, and has since wandered through the galaxy for millions, perhaps billions of years. Its passage through our neighborhood is simply a chance encounter, a visitor from afar, not a manufactured object or an artificial probe. This view is the orthodox stance, and it is the one most often articulated by NASA and other scientific institutions in their official statements. It's also the default assumption of most professional astronomers when asked about such objects. This perspective isn't merely rooted in institutional inertia or a reluctance to entertain alternative hypotheses. It is supported by positive, tangible evidence. For example, the James Webb Space Telescope has detected in the coma of 3I Atlas a mixture of gases: water, carbon dioxide, carbon monoxide, and carbonyl sulfide, as well as tiny ice grains. These components form the familiar cocktail of volatiles that we expect from a typical comet. Such substances are known to originate in the cold depths of space, condensing into icy solids far from the warmth of stars, and then sublimating, turning directly from solid to gas when heated by starlight as the object approaches the sun. The spectral signatures observed by JWST match laboratory data with high confidence, leaving no ambiguity about their molecular identities. This reinforces the natural origin hypothesis. The gases and ice grains are consistent with what we know about cometary composition. However, there remains a significant puzzle, namely, the ratio of these gases. Specifically, the fact that carbon dioxide is observed at a ratio of about 8 parts for every water molecule is strikingly unusual. In our solar system, hundreds of comets have been studied, and when they become active near the sun, water overwhelmingly dominates their volatile output. Typically, the ratio of carbon dioxide to water is much less than 1, with perhaps 1 molecule of CO2 for every 10 or 20 molecules of H2O. Even among the more CO2-rich comets we have identified, such as C2001A2 or C199501 Hale-Bopp, the ratios rarely exceed a 1-to-1 balance. They follow a familiar trend with water remaining the dominant volatile, but 3I Atlas defies this pattern. It is producing 8 times more carbon dioxide than water. Such a deviation is not just a minor anomaly, it is statistically significant, a staggering 6 standard deviations above the mean, analogous to a medical diagnosis where a slight elevation in cholesterol becomes a clear indicator of an underlying condition. This discrepancy compels us to seek an explanation. One plausible hypothesis involves the formation environment of the object itself. In the early stages of planetary system development, a protoplanetary disk exhibits a temperature gradient decreasing with distance from the host star. Close in, the environment is hot and dominated by rocky material, where ices cannot condense. Farther out, beyond a certain snow line or frost line, which typically lies a few astronomical units from the star, water ice begins to condense and accumulate. As you move even further away, temperatures drop further, enabling the condensation of more volatile ices like carbon dioxide and at even lower temperatures carbon monoxide. If 3I Atlas formed in a region of its birth disk that was just cold enough to allow copious CO2 ice formation, but where water ice had already been depleted, perhaps locked inside minerals or otherwise unavailable, it would naturally develop a composition enriched in CO2 relative to water. This kind of compositional zoning is not just theoretical. It has precedent within our own solar system. Kuiper belt objects, for example, show variations in their ice content depending on their formation locations, with some bodies being richer in methane or nitrogen ices, reflecting their original thermal environments. In essence, the unusual chemical signature of 3I Atlas could be a direct imprint of where and how it formed, a natural consequence of the conditions that prevailed in its parent protoplanetary disk. Such a scenario aligns with our understanding of planetary system diversity and the processes that lead to comet formation elsewhere in the galaxy. In different star systems, the distribution of volatile compounds within small celestial bodies isn't uniform, but varies considerably. Some objects are predominantly water-rich, while others contain a higher proportion of methane or nitrogen ice. This heterogeneity stems from the diverse formation environments and thermal histories of these bodies. When we consider extrapolating this to a star system with a different stellar mass, the associated temperature profile of the protoplanetary disk would shift accordingly. A star with a different mass influences the temperature gradient and the location of the snow line, the boundary where particular ices condense, altering the chemical makeup of forming bodies. Moreover, differences in metallicity, the abundance of elements heavier than hydrogen and helium, can further impact the types of volatiles that dominate. For example, in such a system, conditions might favor the formation of carbon dioxide-rich bodies over those rich in water, simply due to the local chemistry and thermal environment. Adding another layer to this complexity is the radiation processing hypothesis, which provides a plausible explanation for the altered surface chemistry of interstellar objects like 3I Atlas. Suppose this object has spent around 10 million years drifting through interstellar space. During that time, it would have been subjected to relentless bombardment by cosmic rays. High-energy protons and atomic nuclei accelerated by violent astrophysical phenomena such as supernova remnants, and immersed in ultraviolet radiation from distant stars. These energetic particles and photons penetrate the surface layers, breaking molecular bonds and inducing chemical transformations. Water molecules, for instance, can be split into hydrogen and oxygen, leading to the depletion of surface water ice and the creation of other compounds. Simultaneously, the radiation can break down or convert carbon dioxide into different chemical species. Importantly, this radiation doesn't just alter surface chemistry. It also fosters the formation of an insulating crust. This crust, composed of processed, less volatile material, acts as a barrier that reduces the sublimation of underlying ices. Water ice and carbon dioxide ice, however, have different sublimation behaviors, or sublimation curves. Water begins to outgas significantly at temperatures between approximately 150 and 200 Kelvin. Carbon dioxide, on the other hand, sublimates at slightly lower temperatures, around 150 Kelvin and below. If the crust formed by radiation acts as an insulator, it can allow the outer layers to warm enough to release carbon dioxide while still trapping the water ice in the depths. This process results in the preferential venting of carbon dioxide despite the presence of substantial quantities of water inside the nucleus. Essentially, the nucleus behaves like a thermos bottle with a leaky cap, where the leak favors the more volatile species. This model helps explain why, at the current state, the ratio of carbon dioxide to water might be unexpectedly high. As the object approaches the sun, however, solar heating penetrates deeper, potentially causing the internal water to outgas more freely. If observations show the ratio shifting toward increased water activity near perihelion, it would lend support to the radiation crust model. Conversely, if the ratio remains stubbornly CO2-rich despite increasing solar warmth, that would suggest the object's composition is intrinsically dominated by carbon dioxide. Now, addressing the apparent acceleration paradox, the observation that the object exhibits outgassing activity yet shows only minimal non-gravitational acceleration, can be explained through the concept of balanced jets. Comet nuclei are far from perfect spheres. They are irregularly shaped with valleys, cliffs, craters, and plains. Many regions are cloaked in dust, which insulates the underlying ice, while other areas expose ice or thin layers of dust that allow sublimation. When sunlight strikes these active regions, it triggers gas jets that carry dust particles outward, producing thrust much like a tiny rocket engine. If multiple jets are firing from different parts of the nucleus, their thrust vectors can be oriented so that they almost cancel each other out. This means the total outgassing activity can be very high, producing a significant amount of gas and dust, but the net force imparted in any particular direction remains small. This scenario isn't purely hypothetical. The Rosetta spacecraft's observations of Comet 67P Churyumov-Gerasimenko demonstrated this phenomenon. The comet had several active regions with jets firing from the neck and lobes, resulting in a measurable but modest non-gravitational acceleration. The distribution and orientation of these jets effectively balanced each other, producing a subtle push despite intense activity. In essence, the nucleus acts like a system of multiple tiny thrusters arranged such that their collective forces neutralize each other's influence on the comet's overall trajectory. This balanced jet mechanism offers a natural explanation for how a highly active comet can exhibit surprisingly weak non-gravitational acceleration. An elegant solution that aligns with observed behaviors in our solar system's comets. If the asymmetric coma observed by JWST in the case of 3I Atlas results from multiple jets emanating from different regions on its nucleus, jets arranged so that their lateral or horizontal components effectively cancel each other out, while their vertical components combine to produce the distinctive shape of the coma, then all the physics and mathematics align perfectly to produce the phenomena we are witnessing. This scenario, though requiring a precise and perhaps delicate geometric arrangement, is not inherently implausible because cometary nuclei are known to come in a vast array of shapes and sizes with diverse jet activity patterns. Such a configuration could naturally account for the observed high activity levels, an active, dramatic coma, while simultaneously generating only a minimal net force, resulting in the weak non-gravitational push that we've measured. The calculations and physical principles involved support this explanation, and given the natural variability in comet structures, it remains within the realm of possibility. However, an honest and rigorous scientific assessment must confront a significant issue. The lower limit estimate of the object's mass, approximately 33 billion tons if we accept it at face value, implies a minimum diameter of about 5 kilometers, assuming a typical cometary density. This is no small size. Comparing with well-studied comets in our solar system, Halley's Comet measures roughly 15 kilometers in length but averages about 8 kilometers in width, making it somewhat smaller than this estimate. Hale-Bopp, one of the most spectacular comets observed in recent history, was approximately 60 kilometers across. So while a 5-kilometer object is substantial, certainly within the realm of known comet sizes, it is nonetheless notable, especially since it ranks as only the third confirmed interstellar object ever detected. This leads us into the realm of statistical curiosity. Finding a 5-kilometer-sized interstellar object as one of only 3 detections is unusual. The common understanding, based on models of planetary system formation and debris distribution, suggests that smaller debris objects should vastly outnumber larger ones, following a size-frequency distribution characterized by a steep power law slope. Therefore, our detection of a relatively large object early in the survey might seem improbable without some bias. The selection effect argument provides a natural explanation. Our current surveys tend to favor the detection of brighter objects, and brightness depends on both size and activity level. An object that is small but highly active could outshine a larger dormant asteroid, making it more likely to be spotted. Consequently, we might only be seeing the tip of the iceberg, with countless smaller, fainter interstellar objects passing unnoticed. As observational technologies improve, particularly once the Rubin Observatory, formerly LSST, comes online, our ability to detect smaller and less active objects will increase, and the observed size distribution should begin to align more closely with natural expectations. The early discovery of a large interstellar object, then, could merely reflect luck, whether good or bad, depending on one's perspective. On the other hand, skeptics argue that if 5-kilometer interstellar objects are common enough to have been detected in a mere handful of observations, so much so that we've already encountered one in every 3 detections, then the overall population of interstellar debris must be disproportionately skewed toward large objects. Such a scenario conflicts with most models of planetary system formation, which predict that small debris should be vastly more numerous than large bodies, often following a power law distribution with a steep slope favoring small sizes. The likelihood of detecting large objects early at a rate that suggests they are far more common than models anticipate is statistically low. Thus, either our models are incomplete or incorrect, or our sample size is simply too small to draw firm conclusions. Alternatively, there might be something inherently unusual about the objects we've detected. Perhaps they are not representative of the typical interstellar debris population. Looking ahead, what could future observations from Mars and perihelion passage tell us? If we observe the jet structures evolving in a way that correlates predictably with the solar angle, meaning that the jets shift position or activity levels as the object approaches the Sun, that would be strong supporting evidence for a natural cometary origin. Such behavior aligns with what we see in solar system comets, where solar heating drives active jets that respond predictably to illumination changes. Moreover, if the ratio of carbon dioxide to water begins to shift toward more water as the object heats up, consistent with the radiation crust model, then that would further support a natural explanation involving a surface crust that insulates water ice beneath. Conversely, if measurements of the rotational period suggest a tumbling, irregular shape consistent with a natural fractured nucleus, that would reinforce the natural comet hypothesis. On the other hand, if activity remains strangely uniform regardless of the changing solar illumination, or if the comet's structure and composition fail to evolve as models predict, then that would challenge the natural explanation and invite consideration of alternative hypotheses, including artificial origins. In essence, these upcoming observations will be critical. They can either reinforce the natural comet hypothesis by showing predictable thermally driven behavior, or reveal, if we observe jet activity that appears disconnected from the influence of sunlight, that inevitably raises eyebrows and prompts further questions. Such behavior defies the typical expectations for natural objects, where jets and outgassing are directly tied to solar heating. Similarly, if the object's brightness or spectral signatures shift in ways that cannot be explained by thermal processes, say, sudden fluctuations in emission lines or brightness not aligned with expected solar-driven sublimation, that signals something unusual and warrants scrutiny. Another crucial point to emphasize is the safety of Earth. The closest approach of 3I Atlas to our planet in December will be approximately 270 million kilometers, vastly distant in cosmic terms. To put that into perspective, Mars comes as close as about 55 million kilometers to Earth at its nearest, and our Moon is merely roughly 400,000 kilometers away. Given these distances, 3I Atlas is nowhere near a collision course. Even if by some chance our estimates of its size are significantly off, or if it fragments into multiple pieces, these fragments would still remain far outside Earth's orbit. They would not intersect with our planet's path, ensuring no threat or risk of impact. This assurance is vital because sensationalist narratives about impending doomsday comets or impending alien invasion fleets tend to generate buzz and clicks, yet they do a disservice to the public's understanding of actual risk. The reality is straightforward. The probability of an impact from 3I Atlas or any similar object in this context is zero. Not low, but zero. Therefore, the traditional comet hypothesis remains the most plausible explanation, resting on solid scientific footing. Its unusual chemistry, such as a high ratio of carbon dioxide to water, combined with the observed weak non-gravitational acceleration, which can be explained through balanced jets or the possibility of a very high mass and its interstellar origin, consistent with known ejection mechanisms, make it the simplest and most consistent explanation of all the data so far. The observable coma, rich in natural volatiles like water, carbon dioxide, and carbon monoxide, further supports this natural origin hypothesis. While the uncertainties about the precise size and mass are still present, they are not sufficient to disprove the comet model. In fact, the overall picture aligns well with what we expect from a natural interstellar object, simple, elegant, and fitting most of the observed phenomena. Yet it's important to recognize that simplicity does not equate to certainty. Scientific hypotheses are always provisional and subject to revision in light of new evidence. There are, however, serious scientists, credentialed and experienced, who argue that we should at least entertain the possibility that our measurements might be based on the wrong assumptions. They suggest that perhaps we are not looking at a natural object at all, but rather at an artifact, an intentionally or unintentionally constructed object of extraterrestrial origin. This leads us to what is known as the mothership hypothesis, or more broadly, the artifact among the stars. This idea takes us into deeper, colder waters of speculation. The hypothesis posits that 3I Atlas might not be a naturally occurring comet, but rather a piece of technology, an interstellar probe, perhaps dormant or possibly still operational, that has been passing through our solar system. It might be a long-lost artificial craft that just happens to resemble a comet, mimicking outgassing behavior or other natural signatures convincingly enough to evade detection as an engineered object. It's crucial to clarify from the outset that this is not the mainstream view. It is not the position held by NASA or most astronomers. Instead, it is a topic of discussion primarily among a few researchers, notably Avi Loeb and colleagues, who believe that considering such alternatives is an essential part of scientific inquiry, even if ultimately rejected. Science advances through exploring all plausible hypotheses, not dismissing them outright. At the core of the artifact hypothesis are two main points: statistical rarity and anomalous behavior. Loeb and others argue that based on naive statistical models, we should expect to encounter many small interstellar objects before finding a larger one. The size distribution of natural debris ejected from planetary systems should heavily favor small fragments, pebbles, rocks, and minor asteroids, because smaller objects are far more numerous. In that context, discovering a 5-kilometer-sized interstellar object as only our third confirmed detection appears suspiciously rare, akin to casting 3 fish from the ocean and unexpectedly catching a whale. While possible, such an occurrence suggests that perhaps our understanding of the population is incomplete or being mischaracterized. This statistical anomaly is a compelling piece of the puzzle for proponents of the artificial origin hypothesis. If such large objects are unexpectedly common relative to natural expectations, it hints that we might be missing something fundamental about their origin, or that they are not entirely natural in origin at all. Many astronomers challenge this line of reasoning, emphasizing the profound influence of detection biases. They highlight that our observational surveys are inherently skewed towards spotting larger objects because these bodies are brighter and easier to detect from afar. The surveys that have identified interstellar visitors like Oumuamua, Borisov, and now 3I Atlas are primarily limited by their sensitivity thresholds. They tend to pick up only the most luminous, conspicuous targets lurking in the vastness of space. As technological advancements continue at a rapid pace, our capacity to detect smaller, dimmer interstellar objects, those that are currently beyond our reach, will improve. Over time, the distribution of sizes among these objects should begin to resemble the natural population more closely, leading to what is known as normalization in the size spectrum. In essence, the so-called whale, the large, easily detectable objects, is not necessarily rare in the universe. It's simply the only type our current instruments are capable of catching with the existing observational scope. The larger bodies dominate our current detections because they outshine their smaller counterparts, much like a fishing net with a coarse mesh only catches the biggest fish. Acknowledging this, Loeb concedes that detection bias plays a significant role, but he contends that even after factoring in these biases, the numbers remain compelling enough to warrant heightened scrutiny. The second pillar of his argument revolves around the observed weak non-gravitational acceleration of the object, an intriguing anomaly considering the clear evidence of outgassing. We've previously discussed the natural explanation involving balanced jets, localized regions on the comet's surface that eject material in such a way that their thrust vectors cancel out overall, resulting in minimal net acceleration despite active outgassing. While this explanation remains plausible, Loeb points out that it necessitates a very specific, somewhat contrived geometric arrangement. Multiple active regions would need to produce thrust vectors aligned in such a precise manner that they offset each other perfectly, which is theoretically possible but verges on a just-so story, a narrative that requires fine-tuned conditions unlikely to occur naturally without some form of underlying pattern. Alternatively, if the object isn't outgassing due to thermal sublimation, the typical natural process, then perhaps it's venting material deliberately for other reasons. This could be for propulsion, internal thermal regulation, or some form of active control. In such a scenario, the visible coma, clouds of expelled material, would be evidence of venting, but the net acceleration could still be minimal if the venting is carefully managed or symmetrically arranged. Controlled or symmetric venting would produce a visible outgassing profile while effectively maintaining a stable trajectory, not unlike a spacecraft carefully balanced to avoid unintended acceleration. The third pillar concerns the trajectory of the object itself. Here, caution is warranted because the data does not definitively support the idea that 3I Atlas's path is anomalous. Its orbit appears to be hyperbolic, which aligns with an interstellar origin, and the inclination and approach angle fall within the expected range for a naturally arriving object that has not been specifically directed or manipulated. It's approaching from a direction and at a velocity consistent with a random passage through the galaxy, not a deliberate probe making a calculated approach. The trajectory exhibits no signs of deceleration, active maneuvering, or course corrections that would indicate an artificial origin. However, proponents of the artificial hypothesis note that if one were designing a stealth probe, an autonomous craft sent from an advanced civilization, one might intentionally avoid obvious maneuvers or signatures that could betray its artificial nature. Instead, such a probe might coast passively along a trajectory that appears entirely natural, minimizing any detectable signals or outgassing patterns that would reveal its true nature. It might vent material in ways that mimic natural cometary outgassing, with the goal of passing unnoticed while gathering data. This means the absence of overt technological signatures doesn't necessarily prove naturalness. Rather, it could indicate sophisticated engineering aimed at concealment. This line of reasoning, however, is inherently unfalsifiable, a major challenge in scientific inquiry, because it relies on assumptions that cannot be definitively proven or disproven. If an object exhibits no signs of maneuvers or technological signatures, some argue it's natural. If it does, it's artificial. The absence of evidence in this case isn't evidence of absence, and the debate hinges on what kind of evidence would be considered definitive. So what would constitute compelling evidence for the artifact hypothesis? The most straightforward indicator would be the detection of repeatable, unmistakable maneuvers, any change in trajectory that cannot be accounted for by outgassing or natural forces. For example, if 3I Atlas were to alter its course unexpectedly, accelerating or decelerating in a manner inconsistent with natural physics, this would be a smoking gun, a definitive signal of artificial control. Such an anomaly would stand out sharply against the natural background and could not be explained away by natural processes. Another potential signature would be the observation of specular reflections. Perpendicular to the sun's trajectory, if an object were to execute a course correction that precisely aligned it toward a specific target, something that would defy natural explanation, it would represent a phenomenon utterly inexplicable by known natural processes. Similarly, the presence of specular reflections or panel glints, sharp, bright flashes of light, would be a significant clue. Natural celestial bodies tend to be irregular and rough in shape, scattering sunlight in diffuse, unpredictable ways. In contrast, manufactured surfaces such as solar panels or reflective mirrors can produce concentrated mirror-like reflections when sunlight strikes them at particular angles. If photometric data captured a sudden, brief spike in brightness that repeated periodically, matching the object's rotation, it would strongly suggest the presence of flat reflective surfaces designed for optimal light reflection, characteristics typical of engineered structures rather than natural bodies. Furthermore, the detection of narrow band transmissions, specific concentrated signals at distinct frequencies, would be compelling evidence of artificial origin. Comets naturally emit broad-spectrum thermal radiation and scatter sunlight, producing wide-ranging spectral signatures. They do not, however, emit signals at precise, narrow frequencies that are not associated with natural molecular lines. Therefore, if radio telescopes observed a consistent narrowband signal from 3I Atlas at a frequency that does not match any known natural molecular emission, it would constitute extraordinary evidence pointing toward technological activity. Additionally, infrared observations revealing the object to be warmer than what solar heating alone could produce might suggest internal power sources. Such internal heat could result from radioactive decay or tidal forces, but ruling out these natural processes would be necessary before considering artificial power generation. As of now, none of these possible markers, unusual reflections, narrowband signals, or excess thermal emission, have been observed. The object's trajectory remains ballistic, with no reported glints or reflections beyond what one would expect from a dusty, icy surface. Likewise, no radio signals have been detected, and the thermal profile, to the extent it has been measured, aligns with the expected heating from sunlight. In response, Loeb's stance is essentially to continue the search. He emphasizes that the cautious attitude or stigma surrounding the hunt for technosignatures has led astronomers to underinvest in the types of observations that could reveal alien technology. If nobody actively searches for unusual maneuvers, signals, or reflections, then the chances of discovering them diminish drastically, no matter their existence. Loeb champions a more aggressive approach, increasing observational frequency, enhancing the resolution of measurements, expanding the spectrum of wavelengths monitored, and conducting systematic targeted searches for signs of artificiality. He argues convincingly that assuming everything is natural, without actively looking for signs of technology, guarantees that we will never detect such signs, even if they are present. This approach echoes a historical precedent set during the case of Oumuamua. When it first exhibited an unexplained acceleration, an anomaly that challenged natural explanations, Loeb and his colleague Shmuel Bialy published a paper proposing that Oumuamua might be a light sail, a thin reflective sheet propelled by radiation pressure from the sun. They suggested that if Oumuamua were artificially constructed similar to a piece of aluminum foil, it could be accelerated in a manner consistent with the observed trajectory. Importantly, their publication was carefully framed. The light sail hypothesis was presented as one of several possibilities, not as a definitive conclusion. The reaction, however, was swift and polarized. Some media outlets sensationalized the story with headlines proclaiming that Harvard scientists had declared Oumuamua an alien spacecraft. Meanwhile, many astronomers pushed back vigorously, emphasizing that natural explanations, such as hydrogen outgassing or nitrogen ice sublimation, remained far more plausible. The debate became heated, sometimes personal, with accusations flying. Loeb was criticized for seeking attention, while critics were accused of dismissing the possibility of alien technology out of closed-mindedness. This episode exemplifies the tension between open scientific inquiry and the caution necessary to avoid unwarranted speculation, highlighting the importance of framing hypotheses carefully and responsibly. The intertwining of scientific inquiry with media narratives and institutional politics has often led to a tangled web of interpretations and priorities. What is crucial to understand from this complexity is that extraordinary claims, such as the existence of alien artifacts, do indeed demand extraordinary evidence. This principle, rooted in rigorous scientific methodology, emphasizes that without compelling proof, skepticism remains justified. However, it is equally important to recognize that this high standard should not become a barrier to considering even the faintest possibility. If one begins with the assumption that the prior likelihood of extraterrestrial artifacts existing is absolutely zero, meaning that by definition the probability is dismissed entirely, then no amount of subsequent evidence could ever be sufficient to alter that belief. This approach essentially dismisses the possibility before any data can be examined, turning scientific skepticism into dogma. Such a stance is antithetical to the scientific process, which relies on openness to new evidence and continuous updating of hypotheses. A more rational and scientifically responsible position is to assign a very low but non-zero prior probability to the existence of alien technology. From this baseline, the accumulation of data, whether confirming natural origins or hinting at artificiality, serves to refine our beliefs. Loeb's framework exemplifies this approach by formalizing the process of updating our confidence level based on incoming evidence, allowing for a nuanced assessment rather than a binary judgment. Current observational data strongly favor the natural cometary model over the artificial hypothesis. The spectral signatures detected by instruments like the James Webb Space Telescope reveal a composition dominated by natural volatiles, primarily water, carbon dioxide, and simple organics, that align perfectly with what we expect from icy bodies formed in space. Moreover, the physical behavior of the object, its shape, the way it evolves as it approaches the sun, and the observed activity are consistent with typical comet-like phenomena. In other words, everything measurable about this object points towards a natural origin, and applying Occam's razor, preferring the simplest explanation, leads us to conclude that it is most likely a comet. However, it is important to recognize that Occam's razor is a guideline, not an immutable law. Loeb himself cautions that the simplest explanation can sometimes be wrong. Nature is often more intricate than our assumptions, and what appears simple might conceal complexity or deception. This leads us into the ongoing tension between media representations and scientific prudence. Major space agencies like NASA and ESA, along with most academic researchers, tend to approach reports of strange objects with caution. Part of this is responsible communication. There is no current evidence indicating hostile intent or behavior, and labeling something a threat without basis risks unnecessary panic. Pointing out that an object is not on a collision course and exhibits no aggressive actions is a form of responsible restraint. It counters fear-mongering and maintains public trust. Nonetheless, there is also an element of institutional conservatism. Space agencies operate under the scrutiny of public funding and reputation. Scientists are cautious because making a premature or unfounded claim could damage careers and credibility. As a result, the tendency to err on the side of caution can inadvertently suppress legitimate scientific inquiry into edge cases, those anomalies that defy easy explanation but might in fact be truly extraordinary. The possibility that a craft is deliberately masked as a natural object, such as a comet, remains within the realm of theoretical plausibility. An advanced technology could, in principle, be engineered to mimic natural volatiles, venting gases like water, carbon dioxide, or simple organics. These gases can be synthesized or stored, and their release could be carefully controlled to prevent detectable acceleration or maneuvering signals. The probe could be shaped to minimize radar reflections and optical regularities, and it could emit thermal radiation consistent with passive solar heating. The concept of a lurker probe, a stealthy autonomous device left by an advanced civilization, fits into this speculative framework. Such probes might drift passively through the galaxy, collecting data without broadcasting signals or performing overt maneuvers. They would remain dormant until some trigger prompts activity, avoiding detection by not actively revealing their presence. In the dark forest scenario of the cosmos, where civilizations hide to avoid potential threats, such stealthy probes make strategic sense. They gather intelligence while minimizing risk of detection or conflict. This raises profound questions about how we interpret the universe. The absence of concrete evidence for artificial origin does not necessarily mean such objects do not exist. It might simply indicate that they are designed to conceal themselves. Conversely, current observations align well with natural explanations, and the caution exercised by mainstream science reflects a commitment to empirical rigor. Nonetheless, the theoretical possibility remains, and the debate continues as new data arrives. In essence, the scientific approach advocates for an open-minded yet skeptical stance, being willing to entertain hypotheses without prematurely dismissing them, and updating beliefs as evidence accrues. This balance is vital in the search for extraterrestrial intelligence, where the stakes are high and the clues subtle. The ongoing dialogue between scientific prudence and the allure of discovery drives us. You can conceive of intelligence existing without any direct exposure, but therein lies the fundamental problem. This idea is dangerously adaptable, almost infinitely so. Any object, be it natural or artificial, can be interpreted as a lurking probe if one is willing to assume the existence of hyper-stealthy, almost mythical engineering capabilities. This flexibility renders the hypothesis unfalsifiable, and in scientific discourse, hypotheses that cannot be tested or potentially disproven are inherently of limited utility. Science thrives on predictions that can be observed, measured, and potentially contradicted, and thus, unfulfillable hypotheses are more akin to philosophical musings than scientific tools. Loeb's contribution in this context is to attempt to make these predictions explicit and operational. The strategy involves searching for tangible signs, maneuvers that indicate deliberate course adjustments, reflections that suggest artificial surfaces, or emissions such as radio signals, each serving as potential evidence of an artificial origin. If these searches come up empty, the hypothesis naturally weakens, gradually losing credibility. If, however, they yield positive results, the case for artificiality gains strength, forcing us to reconsider our assumptions. Policy considerations also come into play here. Suppose there were even a modest 10% probability that 3I Atlas is an artifact rather than a natural object. In that scenario, how should space agencies respond? Should they prioritize close-up imaging to gather detailed visual data? Should efforts be made to establish communication channels, sending signals or attempting contact? Or should protocols be activated to intensify tracking and monitoring, to observe any subtle changes or behaviors? Currently, space policy lacks a comprehensive framework for handling such potential encounters with extraterrestrial probes. The Outer Space Treaty, for example, primarily addresses issues of territorial claims and weaponization in space, but it offers little guidance on the detection, identification, or response to alien artifacts. On the other hand, SETI, Search for Extraterrestrial Intelligence protocols, do exist for responding to detected radio signals. These are voluntary international guidelines that have yet to be tested in a real-world scenario. Within this debate, notable scientists like Jason Wright of Penn State have voiced skepticism towards some of Loeb's specific claims, particularly regarding the size estimates and statistical interpretations. Wright argues that Loeb may be overanalyzing noisy data, and that the size-frequency distribution of interstellar objects doesn't withstand rigorous scrutiny once all selection effects and uncertainties are properly accounted for. This is a healthy, necessary part of scientific discourse, not personal antagonism. It demonstrates that the community is actively scrutinizing the assumptions, models, and interpretations, which is essential in advancing understanding. So after tonight's passage of Mars, where does the mothership hypothesis stand? If no deliberate maneuvers are observed and the object's behavior continues to align with natural outgassing patterns, and if perihelion passes uneventfully without any surprising activity, the probability that it is an artifact will decline further. In terms of Loeb's scale, its rating should continue to drop. However, unless we manage to image the nucleus directly, resolving its structure at close range, or detect unmistakable signs of technology, we cannot entirely dismiss the hypothesis. That persistent uncertainty, a kind of scientific ghost, remains in the background, floating unseen but ever present in the data. Moving to the third scenario, a hypothesis both more plausible and more unsettling than the idea of a mothership. The notion that the observed object is neither a natural comet nor a functioning alien probe, but rather a fragment, an accidental relic of something once more complex. This is the realm of the debris field hypothesis, intertwined with the dark forest debate about cosmic silence and deliberate concealment. The core question is, if some interstellar visitor turns out to be artificial, why are they silent? Why isn't there any form of communication? Why don't they say hello? The answer, as framed by the dark forest hypothesis, depends heavily on one's philosophical outlook about extraterrestrial life. This hypothesis, popularized through science fiction, most notably by Liu Cixin's trilogy, posits that the universe is a dangerous place, filled with civilizations that are all hiding from each other, because revealing oneself might mean destruction. In this view, silence and stealth are the only rational strategies for survival, leading to a universe where intelligent species remain mute, cloaked in secrecy, lest they become targets of predation or annihilation. This perspective suggests that any interstellar probe, if it exists, might deliberately avoid active communication, instead opting for passive observation while blending seamlessly into the cosmic background. Such a craft, or debris remnants thereof, would be designed to mimic natural objects, disguising its origin through stealthy, low-profile behavior, so that it remains undetectable or unremarkable from our vantage point. If that's the case, then the absence of technosignatures, deliberate signals, or obvious engineering features does not disprove its artificial origin. Rather, it supports the idea that it is intentionally hiding. However, this line of reasoning introduces a profound philosophical and scientific challenge. The cosmos is teeming with the potential for intelligent civilizations, yet paradoxically they all seem to be hiding behind an invisible veil. Why would such civilizations choose silence in an environment seemingly ripe for contact? The prevailing answer lies in the harsh logic of survival. To reveal oneself might be to invite destruction. Any sufficiently advanced society capable of detecting signals from others could, in turn, be capable of perceiving those signals as threats or opportunities, and might eliminate the source to secure its own dominance. As a result, the most prudent strategy for survival, perhaps the only one, becomes total silence. Listen carefully, but never broadcast. Observe keenly, but never reveal your true position. This bleak yet rational outlook paints the universe as a vast, shadowed forest, not because the forest is devoid of life, but because all its inhabitants are crouched behind the trees, holding their breath, watching and waiting in fearful silence. It's a haunting vision, one where the darkness isn't due to emptiness but to a collective choice to stay hidden. While most scientists regard this dark forest hypothesis as a philosophical thought experiment rather than a literal description of galactic sociology, it offers valuable insights into why we detect so little beyond our own signals. Silence in this context is ambiguous. It could mean that no one is out there, or that everyone is out there cloaked in stealth, unwilling to make their presence known. If the dark forest hypothesis holds true, then even if we encountered an alien object like 3I Atlas, its behavior would be consistent with this strategy. It would not broadcast any signals, nor would it perform maneuvers that shout, "Look at me." Instead, it would resemble a natural object, blending into the cosmic background, passively gathering data and quietly moving on. Under such a stealthy approach, our failure to detect technosignatures is entirely expected, not evidence of absence. It's precisely what such a clandestine civilization would intend. But therein lies a profound challenge. This line of reasoning makes the artifact hypothesis unfalsifiable. If the presence of artificial signatures would prove an object is a craft, but their absence is also consistent with the object being a craft, then what observation could ever conclusively disprove the hypothesis? This creates a logical trap, one where the hypothesis survives all conceivable outcomes. While this might be emotionally tempting for those eager to believe in extraterrestrial visitors, it is scientifically sterile. Good scientific inquiry demands the ability to test and falsify theories. Without this, hypotheses devolve into unfalsifiable conjectures. To navigate this, some researchers like Avi Loeb advocate for a probabilistic approach rather than a binary yes or no stance. Instead of asking outright, "Is it alien?" Loeb frames the question as, given the current evidence, how likely is it that this object is artificial? This probability, which he assigns on a scale from 0 to 10, can shift as new data becomes available. Early on, with limited information and several anomalies, a moderate probability might be assigned, say a score of around 5 or 6. As further observations reveal behaviors consistent with natural objects, such as typical outgassing patterns or known compositional signatures, the probability diminishes. Conversely, if future data uncovers ambiguous technosignatures, the likelihood can spike upward even to a perfect 10. This dynamic updating framework exemplifies scientific rigor. It recognizes that initial assessments are provisional and subject to revision. For example, if we obtain close-up images of 3I Atlas that clearly display a typical comet nucleus, rocky, irregular, with observable jets, the likelihood of it being artificial plummets towards 0. On the other hand, if the object continues to exhibit behaviors inexplicable by natural models, such as unexplainable maneuvers, unusual spectral lines, or persistent silent reflections, the probability that it's an artifact increases. Most scientists agree that the prior probability of any given interstellar object being artificial is exceedingly low, perhaps 1 in a million or even 1 in a billion, based on our current understanding of the universe and the rarity of such technological signatures. Overcoming this enormous initial skeptic's threshold would require a multitude of independent, compelling lines of evidence pointing convincingly toward technology, not mere anomalies or natural peculiarities. A single anomaly is insufficient. 2 might be coincidences, but 3 or more could begin to suggest a pattern, provided all natural explanations are thoroughly ruled out. This probabilistic, evidence-based approach allows us to remain open-minded without falling into the trap of unfalsifiability. It emphasizes that science isn't about reaching absolute certainty, but about updating our confidence levels as new, better data emerge. The real challenge lies in distinguishing between what is genuinely evidence of extraterrestrial intelligence and what is simply part of the natural variability of the universe. Until then, the silence of the cosmos remains an intriguing puzzle, one that keeps our curiosity alive and our methods sharpened. This brings us into the complex realm of social dynamics and the intricate web of online speculation surrounding celestial visitors like 3I Atlas. In today's digital age, where information travels at lightning speed and rumors can spread just as rapidly as verified facts, the role of amateur analysts, online sleuths, and viral leaks has become increasingly prominent. Every hazy image, every pixelated frame is scrutinized by thousands of curious minds eager to decipher its meaning. A faint, slightly brighter pixel amidst a noisy background might be heralded as a reflective panel, a sign of artificial surfaces. A subtle fluctuation in brightness could be interpreted as a course correction, a deliberate maneuver. Our innate cognitive wiring compels us to identify patterns even in chaos. We see faces in cloud formations, animals in ink blots, and conspiracies lurking in coincidences. This tendency is not born out of malice or deception. Rather, it stems from the fundamental architecture of human perception and cognition. However, this natural predisposition creates a fertile ground for misinformation and sensationalism. In an ecosystem fueled by rapid-fire sharing, claims that suggest an alien probe has been detected can garner millions of clicks overnight. Meanwhile, corrections, explaining that the object is merely a comet with an unusual chemical makeup, struggle to keep pace, often reaching only a fraction of the initial audience. The result is a distorted narrative where unverified claims gain undue prominence, and nuanced scientific explanations are drowned out by the noise. This phenomenon, sometimes called the symmetry of suspicion, poisons public discourse and complicates effective communication between scientists and the broader community. Veteran researchers involved in the search for extraterrestrial intelligence, or SETI, tend to approach these stories with cautious optimism. They recognize the genuine possibility that alien life could be out there, yet they are deeply wary of jumping to conclusions based on incomplete or ambiguous data. These experts have seen many false alarms over the years. For instance, pulsars, rapidly rotating neutron stars, were once mistakenly thought to be alien beacons, earning them the playful nickname LGM, for little green men. It was only after careful study that their natural astrophysical origins became clear. Similarly, the famous WOW signal of 1977, a strong, narrow-band radio spike detected by astronomers, remains unexplained to this day. Despite decades of investigation, it has never been reliably repeated, leaving its true nature unresolved. Likewise, fast radio bursts, or FRBs, initially mystified scientists, sparking speculation about artificial origins. Over time, natural astrophysical sources such as magnetars, highly magnetic neutron stars, have been identified as the culprits. Across the pattern of discovery, a familiar cycle persists. Initial excitement, rampant speculation about extraterrestrial technology, followed by eventual natural explanations that dispel the initial fears. Regarding 3I Atlas, the general consensus within the SETI community remains: show us the data. The community advocates for transparency and rigor. If the object is executing maneuvers, scientists want to see the precise astrometric measurements. If radio signals are detected, they insist on confirmation through multiple independent telescopes to rule out local interference or artifacts. If reflective surfaces are suspected, high-resolution imaging is necessary to verify their existence. Until such concrete evidence emerges, the default assumption remains that 3I Atlas is a natural celestial body, a comet or asteroid passing through our solar system. Now imagine for a moment a hypothetical scenario, one rooted in strategic design rather than coincidence. Suppose you are tasked with creating a stealthy probe to pass through an alien star system. How would you minimize its detectability? First, you would choose a trajectory that avoids the densely populated plane of the ecliptic, the region where most planets and debris orbit. By originating from outside this plane, the craft would be less likely to be spotted by surveys focused on near-ecliptic objects, making detection more difficult and prolonging its covert passage. Second, you would aim to eliminate any energy signatures that might betray its presence. This means avoiding active propulsion systems or radio transmissions which are easily detectable. If the craft needs to vent heat, it would do so in a manner mimicking natural thermal emission, matching the spectral profile of an ordinary celestial body. Third, you would plan the approach so the craft maximizes its observational window without risking collision or detection, timing its closest pass to optimize data collection while staying within a safe distance from potential hazards. Looking at 3I Atlas's actual trajectory, it becomes evident that it does not conform to this hypothetical stealth profile. Its inclination is higher than the ecliptic plane, which is typical for interstellar objects. These bodies are not gravitationally bound to our solar system and thus do not share the orbital plane of the planets. Its approach appears more like a straightforward natural passage rather than a deliberately designed reconnaissance mission. The trajectory does not exhibit the subtle optimizations expected of a craft engineered for stealth or maximum observational efficiency. In essence, the human mind's pattern wreck. The trajectory of 3I Atlas reveals no signs of purposeful design aimed at optimizing observational opportunities. Instead of weaving a complex path that would maximize interactions with planetary bodies or enable strategic vantage points, it follows a straightforward, unadorned course, a direct line passing through the solar system and then out into the dark. If this were a meticulously planned survey, one would expect to see an intentional, perhaps even clever pattern, an orbit that incorporates gravitational assists to alter its trajectory, allowing it to visit multiple intriguing locations or to gather more comprehensive data. Such a trajectory might involve looping around planets or adjusting its path to maximize observational opportunities, much like spacecraft that utilize gravity assists to extend their reach or refine their data collection. But 3I Atlas does none of that. It behaves precisely like a ballistic projectile, an object simply shot through space following the natural laws of motion without any apparent attempt at strategic positioning. This behavior aligns perfectly with what we would expect from an unintentional natural object, something that arrived without a premeditated plan, just passing through the solar system on a hyperbolic path. However, proponents of the dark forest hypothesis, a view rooted in the idea that advanced civilizations deliberately conceal their presence, might counter this interpretation with a different perspective. They could argue that perhaps the goal was not to optimize data collection, but to appear unremarkable, to blend in seamlessly with the cosmic environment. A trajectory that is too clever, one that visits numerous interesting regions or shows signs of deliberate maneuvering, might itself raise suspicion, drawing unwanted attention or confirming an artificial origin. Instead, a simple, uneventful course, an unassuming, boring path, might be the most effective cover, allowing the probe or object to observe without revealing its true nature. This would be a way to operate covertly, sacrificing some data richness for the sake of operational security or stealth. This line of reasoning leads us to a recurring challenge in studying such objects: unfalsifiability. Every piece of evidence we gather can be interpreted in multiple ways depending on the perspective or preconceived notions we hold. If one is inclined to see artificiality everywhere, then even the simplest natural-looking trajectory can be spun into a supporting argument. Conversely, skeptics might dismiss anomalies as natural phenomena or observational artifacts. This flexibility, this ability to interpret the same data to support vastly different hypotheses, means we are not engaging in true scientific testing but rather storytelling. Narratives shaped by imagination as much as by evidence. The influence of social media and algorithmic amplification compounds this problem. Platforms designed to maximize engagement tend to promote content that provokes strong emotional reactions. Claims of alien invasions, secret cover-ups, or cosmic mysteries that stir curiosity and fear. Such sensational claims often garner millions of views and shares, while careful, methodical scientific analyses that emphasize uncertainty and nuance tend to be overshadowed or buried. As a result, the online information environment becomes an echo chamber, where individuals are primarily exposed to content reinforcing their existing beliefs. If someone is convinced that 3I Atlas is a mothership or an alien probe, their social media feeds will likely fill with posts supporting that view. Dramatic headlines, conspiracy theories, and speculative images, while counter-arguments and scientific explanations struggle to reach the same audience. This imbalance is not a new phenomenon but has intensified over the past decade, making effective science communication increasingly difficult. When a viral tweet proclaims, "Harvard scientist confirms alien spacecraft," it captures viewers' attention more readily than a nuanced explanation from reputable scientists emphasizing that the object's behavior is consistent with natural phenomena. The nuance, the uncertainty, and the complexity of scientific reasoning are flattened into sensational sound bites, leaving the public with a distorted and oversimplified picture of what we actually know. So what would disprove the craft hypothesis? That is, what observational evidence could definitively indicate that 3I Atlas is not an artificial object? The answer hinges on specific measurable phenomena. If, after passing perihelion, 3I Atlas continues on a purely ballistic, unaltered trajectory, showing no signs of course correction or maneuvering, that would be a significant strike against its artificiality. Similarly, if its chemistry consistently reveals only natural volatiles, such as water, carbon dioxide, or simple organics, with no detectable signatures of industrial compounds, isotopic anomalies, or other indicators of technological origin, then the case for artificiality diminishes even further. In essence, the absence of detectable engineered signatures combined with a trajectory that aligns with natural expectations would strongly support the hypothesis that 3I Atlas is merely a natural interstellar comet. Conversely, the presence of unexplainable maneuvers, narrowband radio signals, or reflective surfaces incompatible with natural processes would tilt the balance toward an artificial origin, challenging our current understanding of the cosmos. If in the future high-resolution imaging conclusively reveals a nucleus that appears typical, irregular, rocky, and consistent with the known structure of comets, such a discovery would effectively dismiss the hypothesis that 3I Atlas is something extraordinary or artificial. In other words, if the core turns out to be a familiar natural comet, it would be a decisive blow to the idea that this object is an engineered probe or a piece of alien technology. Similarly, if subsequent observations detect multiple interstellar objects exhibiting comet-like behaviors, each with a size distribution fitting well within the statistical expectations for natural ejected debris, the argument that large, rare objects should be improbable becomes void. This would suggest that the apparent rarity of such large objects is simply a statistical artifact, and that our models of natural interstellar populations are correct, reaffirming that we're observing ordinary natural phenomena rather than something extraordinary. Conversely, what kind of evidence would definitively tilt the scales toward an artificial origin? A single unmistakable maneuver, one that cannot be explained by natural outgassing processes, would be a game changer. Think of a sudden course correction or acceleration that defies any known physics of sublimation or jetting. That would strongly suggest deliberate control. Similarly, detecting a radio signal, no matter how brief, at a frequency that cannot be accounted for by natural sources would provide compelling proof. Such a signal would be an unmistakable hallmark of technology. Additionally, the observation of a specular reflection, a bright mirror-like glint, from a flat, smooth surface, or the discovery of geometric structures in high-resolution images would be monumental. These features, if confirmed and reproducible across multiple instruments, would be difficult to explain through natural processes alone and could constitute evidence of artificial design. However, it is crucial to emphasize that a single blurry image or a solitary questionable data point is insufficient to draw firm conclusions. Scientific certainty demands overwhelming and unambiguous evidence, multiple lines of corroboration that are resistant to natural explanations. Our natural tendency as pattern-seeking creatures complicates this pursuit. From earliest times, humans have survived by detecting predators lurking in shadows and interpreting subtle cues. Our brains are wired to find significance even where there is none. This cognitive bias doesn't switch off when we examine distant celestial phenomena. A noisy pixel in an image might be perceived as a panel of a spacecraft. A minor fluctuation in brightness could be mistaken for a maneuver. An unusual chemical ratio might be seen as a smoking gun. These tendencies to see patterns where there are none fuel our anxieties and raise false alarms. Therefore, understanding our innate biases is the first step toward disciplined, objective analysis. Recognizing this, the prudent scientist pauses when feeling the urge to jump to a conclusion. Ask yourself, what would need to be true for this hypothesis to be false? Consider alternative explanations. Demand better, more definitive data. Science is fundamentally the art of avoiding self-deception, because the easiest person to fool in any inquiry is oneself. So where does this leave us in the ongoing dark forest debate as 3i Atlas ventures past Mars? If it's a covert probe, what some call a lurker, it's unlikely we'll detect it unless it performs an overtly artificial action. If it's merely a natural comet, disguised without any obvious signs of engineering, then we must resist the temptation to overinterpret the silence. The absence of technosignatures in itself tells us almost nothing because such silence is compatible with both natural and artificial scenarios. What we truly need is positive, unambiguous evidence, something that conclusively points in one direction. So far, the data currently favor the natural comet-like explanation. Yet there remains a third intriguing possibility, that 3i Atlas isn't a functioning object at all, but rather a fragment, a remnant of something destroyed long ago, somewhere far away. This is the debris field hypothesis, which posits that what we see might be shards from a distant cataclysm. Imagine a planet disintegrating not gradually over eons, but suddenly, violently and catastrophically within hours or days. Perhaps it drifted too close to its parent star, and immense tidal forces tore it apart. Or maybe two planets collided in a cosmic collision at tens of kilometers per second, vaporizing the impactor and shattering the planetary body into a stream of fragments. These fragments could then be drifting through interstellar space, some large enough to be detectable, others too small to see yet. This debris field would be the cosmic equivalent of a shattered world, cast into the dark, floating remnants of planetary destruction. Such fragments, while physically distant and dispersed, could still carry the chemical signatures of their violent origins, enriched in certain volatiles with surface compositions altered by radiation and shock processes. If we are indeed observing fragments from a distant ancient planetary catastrophe, their peculiar chemical ratios, irregular shapes, and the dynamics of their trajectories could all be explained by this violent past. As these fragments drift, their physical states and compositions would reflect the chaotic. Or perhaps a rogue star swept through the system, its gravitational influence violently disturbing the delicate dance of planetary orbits and hurling worlds into chaotic, unpredictable trajectories. Such a tumultuous event could scatter fragments of celestial bodies across interstellar space, perfectly matching what we might be observing now. These large, irregularly shaped fragments, possibly enriched with specific volatile compounds, could be drifting through the cosmos on ballistic paths, trajectories dictated solely by gravity, unbound by the sun's influence. This is known as the debris field hypothesis, and surprisingly, it remains quite plausible under current scientific understanding. We have tangible examples of planetary destruction within our own solar system that lend weight to this idea. The asteroid belt itself might be the residual remnants of a planet that either failed to fully form or was shattered long ago by the colossal gravitational pull of Jupiter. Saturn's iconic rings are almost certainly the debris left behind from a moon that ventured too close and was torn apart by tidal forces, an event well documented and understood in planetary science. Similarly, in distant systems, astronomers have observed tidal disruption events around black holes and stars, where passing objects are shredded as they cross the Roche limit, the critical distance at which gravitational gradients become destructive. The physics behind these processes is well established. When an object approaches a massive body, the difference in gravitational pull across its structure, the gradient, can become so intense that it exceeds the object's own gravitational cohesion, causing it to stretch, crack, and ultimately fragment. These fragments are then expelled at high velocities, some spiraling inward and falling into the star, others escaping into deep space. Now, if the original body was icy, a supersized comet or a small planet with a substantial inventory of volatile substances, the resulting fragments would carry these volatiles with them into interstellar space. But here's the critical question. During the violent process of disruption, the surface layers would be subjected to intense heating, causing partial vaporization of volatile materials like water and carbon dioxide. What remains afterward would be fragments with potentially unusual compositions, perhaps enriched in more refractory, heat-resistant materials on their surfaces, while their volatile-rich interiors remain sealed beneath a crust of processed material. Does this scenario sound familiar? Because it reflects the core idea we've been exploring for 3I Atlas, a fragment that has undergone radiation processing over millions of years in interstellar space, developing a crust that seals in and alters the original volatile ratios. This model suggests that, after such an event, the surface layers could be enriched with refractory compounds, while the interior still harbors a different mix of volatiles. The idea of a tidally disrupted fragment isn't new. Researchers have previously considered that the peculiar elongated shape and unexpected acceleration of the interstellar object, Oumuamua, could be explained if it were a shard from a tidally disrupted body, perhaps a nitrogen ice fragment from a Pluto-like world. Such a fragment would be flat and reflective, capable of being pushed by sunlight, acting as a natural light sail, yet of entirely natural origin. This hypothesis, while not universally accepted, demonstrates that the notion of natural debris originating from catastrophic events in distant star systems has been seriously contemplated within the scientific community. Applying this to 3I Atlas, the model could unfold as follows. A large icy body, perhaps 1,000 kilometers across, ventures close to a star or a massive planet. During its perilous passage, the body is torn apart by tidal forces, producing a debris field, an array of fragments ranging from microscopic dust grains to sizable chunks measuring several kilometers across. These fragments, propelled outward by the violent disruption, then drift through interstellar space, their compositions and trajectories shaped by the original event. When such an object eventually encounters our solar system, it appears as a peculiar, possibly elongated, volatile-rich fragment, an interstellar visitor bearing the scars of a cosmic catastrophe. In this scenario, these fragments are expelled at astonishingly high velocities, tens of kilometers per second, in a variety of directions. Over the course of millions of years, these scattered pieces gradually disperse across space, yet they tend to follow roughly similar trajectories because they all originate from a common event, a catastrophic disruption of their parent body. Some of these debris fragments eventually drift into the vastness of interstellar space, no longer bound by any star's gravity. In this model, the object known as 3I Atlas is one such fragment, a sizable remnant measuring several kilometers across. Its large size suggests it was part of the core of the original body before the catastrophic event occurred. The chemistry of this fragment is dominated by carbon dioxide. It is CO2-rich because the disruption process preferentially stripped away the water from its outer layers, leaving behind the more refractory, deeper-lying ices rich in CO2. This layering is consistent with the idea that the outer crust of the fragment has been heavily processed by radiation, the result of millions of years exposed to the harsh environment of interstellar space. This radiation alters the surface composition further, creating a crust that is chemically different from the pristine interior. When such an object enters our solar system and begins to warm as it approaches the sun, the crust inevitably cracks. The trapped volatile gases, like CO2, water vapor, and carbon monoxide, start to vent outward, forming a coma reminiscent of a comet. However, the chemistry we observe is skewed and unusual because the fragment's violent and atypical history has left it with a surface and interior that deviate from the norm. From a spectroscopic perspective, if this model holds true, we would expect to see the same volatile gases that are already being detected, namely CO2, H2O, and CO. Additionally, we might observe sulfur-bearing molecules such as carbonyl sulfide, which can form under specific chemical conditions. The dust grains in the coma could also display unusual size distributions, remnants of the violent disruption that didn't allow the material to fully reaggregate into a uniform surface. The dust-to-gas ratio could differ significantly from that seen in typical solar system comets, reflecting the fragment's unique formation and evolutionary history. Preliminary observations from the James Webb Space Telescope already hint at some of these characteristics, though the data remains early and not yet definitive. The key outstanding question is the presence or absence of companions, other fragments that may have originated from the same disruption event. If 3I Atlas is part of a debris stream, then logically, there should be other fragments following similar trajectories through space. These objects wouldn't be situated right next to each other but would be dispersed over a large volume, having spread out over time due to the initial explosion and subsequent gravitational influences. While tidal disruption naturally distributes debris across extensive regions, statistical surveys of the sky should, in principle, eventually detect other objects with similar velocities and compositional signatures. To date, no such companions have been reported. No convoy of objects matching the expected profiles has been flagged by our detection efforts. However, this absence of evidence isn't proof of non-existence. It could simply mean that the other fragments are either too small or too faint to be observed with current instruments, or that they follow trajectories that will only pass through our observational windows after many years or decades. Alternatively, it might be that 3I Atlas is a solitary fragment, the only surviving piece of its parent body. From a broader philosophical standpoint, this debris field hypothesis carries significant implications. If 3I Atlas is indeed a fragment from a planet or moon that was destroyed long ago, what we are witnessing is forensic geology, an alien version of archaeological evidence. These fragments are the final remains of a celestial body that met its violent end, perhaps billions of years in the past, in a star system that we may never identify. They are silent witnesses to a cosmic catastrophe, a remnant of destruction that offers us a rare glimpse into processes of planetary disintegration and cosmic violence. In their fragmented state, they serve as a kind of celestial tombstone, carrying the chemical and physical signatures of a world that no longer exists, drifting through the interstellar void with stories of its violent demise. There is an undeniable, deeply poignant quality woven into this scene, a somber reminder that what we observe is in essence a tombstone adrift in the vastness of space. It's a fragment of a world long gone, carrying no signs of life, no stories, no messages, only the residual chemical signature of its violent and catastrophic end. This silent relic stands as a testament to destruction, a remnant of a planetary demise etched into its very molecules. Yet paradoxically, this mournful relic also holds an extraordinary promise for science. If we can decipher the chemical and physical makeup of these fragments, they become invaluable keys to understanding the hidden interiors of planets and distant star systems. We gain direct samples, celestial artifacts formed under conditions vastly different from our own, shaped by unique chemical environments and possibly originating around stars with different metallicities or ages than our Sun. This approach is nothing less than comparative planetology on a galactic scale. Each interstellar fragment we encounter is like a cosmic sample, an artifact from the universe's grand catalogue of planetary formation and destruction. Remarkably, we don't even need to dispatch a spacecraft to retrieve these pieces. They come to us passing through our solar neighborhood, carried by trajectories that bring them within reach. This natural delivery system transforms the way we study the universe. It's as if the cosmos itself is handing us the pages of an ancient interstellar library. This exciting opportunity, however, demands careful risk communication. It's crucial to clarify that even if a fragment like 3I Atlas is a kilometer-sized shard from a once thriving world destroyed in some distant system, it poses no threat to Earth. Its closest approach, about 270 million kilometers, is vast enough to ensure safety. Even if the fragment were to break apart further as it approaches perihelion, a highly unlikely event given the frigid environment at around 1.4 astronomical units, these pieces would remain on the same hyperbolic escape trajectory. The physics of orbital mechanics simply won't allow such fragments to suddenly veer inward toward Earth without a forceful intervention. No rocket, no planetary gravity assist, no natural process would cause a hyperbolic path to turn into a collision course. The laws of celestial motion are steadfast. They don't bend to opportunistic impacts. Addressing the bias inherent in our detection methods, it's worth noting that large fragments are statistically rare, but not impossible. When a catastrophic disruption occurs, such as a planetary collision or an intense tidal event, the resulting debris follows a power law-size distribution, many small pieces and a handful of larger ones. Because larger fragments are easier to spot, they reflect more light and stand out against the cosmic backdrop, we tend to find them first. This detection bias means our current inventory is skewed toward the big, bright pieces. As our observational capabilities improve, especially with ongoing and future surveys, we can expect to uncover the smaller fragments that populate this cosmic debris field. Over time, the apparent scarcity of large fragments will give way to a more complete picture, revealing a continuum of sizes that fill in the gaps in our understanding. Moreover, the statistical and dynamical properties of these fragments can reveal their origins. If these objects arrived in streams, a series of fragments ejected at similar velocities, then their orbital inclinations and arrival times might show loose correlations. The initial disruption imparts a range of velocities, and over millions of years, gravitational influences and galactic tides spread these fragments apart, diffusing their trajectories. Still, patterns can emerge. If upon analysis a subset of interstellar objects cluster in specific parameters, similar velocities, shared compositional signatures, or timing of arrival, this would serve as circumstantial evidence of a common, perhaps even deliberate origin. At present, with only 3 objects observed, we lack enough data for a solid statistical analysis. 3 is simply too small a sample to confidently identify streams or clusters. Yet when the number grows to 30 or even 300, the patterns begin to tell a story. Such a population would allow us to infer the presence of debris streams, remnants of ancient planetary destruction, further transforming our conception of the galaxy. It would show us that the galaxy isn't just a quiet void dotted with dust and hydrogen molecules, but a vast graveyard filled with the shattered remains of worlds, cosmic corpses drifting silently through space waiting to be discovered. We are only now starting to read the epitaphs on this interstellar gravestone, uncovering stories of planetary destruction and rebirth, written in the chemical signatures of fragments floating through the dark. This perspective invites us to see the galaxy not as a sparse, empty void, but as a dynamic, interconnected mosaic of planetary debris, an ancient, ongoing archaeological record that whispers tales of worlds lost to cosmic violence. Each fragment we find is a clue, a puzzle piece, offering insights into formation processes, destructive events, and the evolution of planetary systems across cosmic time. These relics, arriving naturally or perhaps through more mysterious mechanisms, challenge us to expand our. But lurking beneath this seemingly straightforward narrative is a far darker, more ominous possibility, one that has quietly simmered in the shadows of our collective consciousness throughout this entire discussion. What if, contrary to the comforting assumption that these interstellar visitors are isolated anomalies, they are instead the first glimpses of a far more unsettling phenomenon? Imagine for a moment that 3I Atlas is not an isolated fragment but the initial warning shot from a vast ongoing stream. A veritable doomsday stream, if you will. An unthinkable corridor of cosmic debris stretching across the galaxy's dark expanse, filled with remnants of catastrophic events far beyond our current understanding. Let's explore this chilling scenario through the lens of unverified speculation, with the explicit caveat that it remains purely hypothetical. Visualize a star system, perhaps hundreds or thousands of light-years away, that once underwent a calamitous event so immense that it defies human comprehension. It might have been a superflare, an astronomical eruption 1,000,000,000 times more energetic than any solar flare our sun has ever produced, sweeping through the system and sterilizing its inner worlds, while devastating and disrupting the outer planet's delicate atmospheres and surfaces. Alternatively, imagine a colossal collision, an asteroid or planetary scale impact, between two gargantuan planets, unleashing energy millions of times greater than all the nuclear arsenals humanity has ever amassed, casting vast clouds of debris across billions of kilometers in space. Or perhaps a rogue star, a wandering interloper, streaks through this system at incredible velocities, its gravitational tides shredding the planet's moons and smaller bodies into fragments that scatter across the galaxy like cosmic shrapnel. Whatever the catalyst, the outcome is a relentless, sprawling stream of debris, particles ranging from tiny dust grains to chunks spanning dozens of kilometers, all ejected with similar trajectories, all moving outward at tens of kilometers per second. Over millions or billions of years, these fragments gradually disperse, their orbits slowly diverging yet maintaining a loose cosmic kinship, a convoy of destruction drifting silently through the darkness. Now, by the unyielding march of chance, by the very mechanics of the universe, this debris stream begins to intersect with our solar system. It is a cosmic collision course, set in motion eons ago, yet only now crossing paths with our planetary neighborhood. The first of these visitors was Oumuamua, a slender, elongated object that appeared out of nowhere in 2017. The second was Borisov, a classic comet with a familiar water-rich signature detected in 2019. And now, in 2025, 3I Atlas arrives. Yet many experts suspect this is no coincidence, that all three are mere fragments of a much larger ancient debris field. And if this hypothesis holds true, then countless more fragments, some small, some enormous, are still out there, silently traversing the galaxy, waiting for their moment to pass through our view. Most of these pieces will continue their voyage, passing by Earth and its neighbors at safe distances, their paths unlikely to threaten us directly. Indeed, most will miss our planet entirely, slipping through the cosmic void without incident. But statistically, among the countless objects hurtling through the darkness, a few might not. A rare, chilling possibility emerges. Perhaps some fragments are on trajectories that could intersect with Earth's orbit, or at least come dangerously close, setting the stage for an unseen looming threat. This is the essence of the doomsday stream, a speculative, nightmarish scenario that, I must emphasize, remains entirely unverified. There is no concrete evidence linking these objects into a shared debris stream, nor is there any indication that more are imminently approaching. It is a heavily exaggerated worst-case outline, an alarmist's nightmare, that often thrives in online communities that feed on existential dread and the fear of unseen cosmic forces. Yet despite its speculative nature, it warrants honest discussion, because the universe has a history of surprises. The first question to consider is, does this pattern of interstellar objects, Oumuamua, Borisov, and now Atlas, indicate a trend, or can it simply be attributed to improved detection technology? The honest answer leans toward the latter. Over the past decade, our telescopic instruments have become vastly more sensitive. Data processing has accelerated, and automated detection algorithms are smarter than ever before. We are now scanning more of the sky more frequently, with more comprehensive coverage than at any previous time in history. These technological advances mean we are simply more likely to find what's always been passing through space. In this context, the appearance of 3 interstellar objects within a span of 8 years does not necessarily signal an increase in their frequency. Instead, it reflects our elevated ability to detect such objects, an observational bias rather than an intrinsic cosmic shift. This realization is both reassuring and sobering. While it means we are finally seeing these visitors, it does not by itself imply that let's consider the possibility that these 3 interstellar objects originated from a common source, a celestial stream. If this were the case, what specific characteristics would we expect to observe? To start, they should exhibit similar velocity vectors, moving roughly in the same direction at comparable speeds once we account for the gravitational perturbations they've experienced during their passages through our solar system. Their trajectories would bear the signatures of a shared origin, with their velocities aligning within a plausible range of variation dictated by the mechanics of their ejection and journey. Next, their chemical composition should reflect a common formation environment. They would display molecular fingerprints, distinctive spectral lines, that suggest they originated from the same kind of stellar nursery or planetary system, with similar elemental and isotopic ratios. Such compositional similarities would reinforce the hypothesis that they stem from a shared source rather than being random, unrelated visitors. Finally, if these objects are indeed part of a stream, an ongoing flow of debris from a single disrupted or ejected system, their arrival times should not be entirely scattered or random. Instead, their appearances would cluster in specific periods, mirroring the density and distribution of the stream itself. This temporal pattern would be a telltale sign of a coherent origin, with multiple objects arriving in a sequence that reflects the stream's structure and velocity. Now let's examine our 3 interstellar visitors, Oumuamua, Borisov, and 3I Atlas, against these criteria. Starting with their velocities. Oumuamua had a hyperbolic excess velocity of approximately 26 kilometers per second, indicating it was moving swiftly through space. Borisov's speed was slightly higher at about 32 kilometers per second, consistent with expectations for interstellar objects ejected from other systems. 3I Atlas, on the other hand, is traveling at roughly 58 kilometers per second relative to the inner solar system, though after adjusting for solar gravitational influence, its excess velocity appears somewhat lower. These differences are notable but not entirely inconsistent. They are within a plausible range given the diverse mechanisms that can accelerate objects in different stellar environments. So while not identical, their velocities are comparable enough to keep the stream hypothesis on the table. though this constitutes only a weak initial signal. Moving on to composition, Oumuamua revealed no visible coma in our observations, leaving us with very limited compositional data. Some models suggest it might consist of nitrogen ice, while others propose hydrogen ice or even a loosely bound aggregate of dust, what some might call a dust bunny. Borisov, however, was a classic comet, rich in water ice and displaying a typical mixture of volatile compounds similar to solar system comets. 3I Atlas is notably different. It appears to be CO2-rich, with a ratio of outgassed molecules that is distinct from both Oumuamua and Borisov. This diversity in composition suggests a lack of uniformity among these objects, making it less likely they originate from a single coherent stream, especially since natural debris streams tend to share similar properties stemming from their parent body's composition. Therefore, the compositional evidence points more strongly against a common origin. Finally, considering their arrival times, Oumuamua was first detected in October 2017, Borisov followed in August 2019, with its closest approach occurring in December of that year. 3I Atlas was discovered in July 2025, with its closest approach to Mars on October 3rd of this year. The intervals between these encounters are roughly 2 years for the first pair, then a gap of about 6 years before 3I Atlas appears. This irregular spacing does not match the more regular patterns expected from a true stream, where objects would typically arrive in a more synchronized sequence, reflecting the physical distribution and velocity of debris in the stream. The significant gap and lack of consistent timing make the hypothesis that these objects are part of a single debris stream less convincing. In summary, when we scrutinize these 3 interstellar visitors against the key criteria, similar velocities, shared composition, and arrival timing, each point offers only partial support for the stream hypothesis. Their velocities are in the same general ballpark but not precisely aligned. Their compositions are notably diverse, and their arrival intervals are irregular. This weak correlation suggests they are more likely independent arrivals from different origins rather than members of a coherent debris stream. Nevertheless, it's crucial to remember that our sample size remains extremely limited. Only 3 objects. With such a tiny data set, it's impossible to draw definitive conclusions. As our detection capabilities improve, especially with upcoming surveys like the Vera C. Rubin Observatory, we will gather more data. This will enable us to identify potential patterns and better understand whether these objects are truly linked or simply a random sampling of the galaxy's interstellar debris. Impacts from micrometeoroids on spacecraft, especially those exhibiting unusual density or compositional patterns that align with the predicted trajectory of a suspected debris stream, remain an area of active investigation. Similarly, anomalies in the diffuse infrared background, tiny variations in the sky's IR glow, could hint at an unusual concentration of dust particles, perhaps related to this interstellar debris flow. Yet, to date, no such signals have been officially reported. The ongoing searches for these subtle indicators are inherently challenging. The sky is a noisy environment, and these signals tend to be faint and difficult to distinguish from background variations. However, the landscape of detection is rapidly changing with advancements in survey technology. Take the Vera C. Rubin Observatory, for example. It is designed to detect objects down to a magnitude of 24 or 25, an astonishing feat given that the faintest stars visible to the naked eye are at about magnitude 6. To put this into perspective, each step in magnitude corresponds to a brightness change by a factor of approximately 2.5. Moving from 6 to 25 magnitudes means Rubin will be able to observe objects about 400 million times dimmer than the faintest stars we can see without assistance. This extraordinary sensitivity enables the observatory to detect small asteroids, distant comets, and crucially interstellar objects that previous surveys would have completely missed. This leap in capability does more than just increase the sheer number of detections. It fundamentally alters the apparent size distribution of observed objects. Currently, our detection bias favors larger or highly active objects because those are inherently brighter and easier to spot. But Rubin's enhanced sensitivity will begin to fill in the lower end of the size spectrum, revealing smaller and fainter interstellar visitors. If, in the coming years, the number of detected small interstellar objects begins to outnumber larger ones, say dozens of small ISOs for every large one, that outcome would align with natural expectations based on how ejector populations are theorized to form and evolve in planetary systems. Conversely, if the ratio remains skewed toward larger objects, implying an unexpectedly small number of smaller interstellar fragments, this would be profoundly surprising. Such a discrepancy could lend support to statistical arguments suggesting that the population we observe might not be entirely natural, raising questions about the origins and distribution of interstellar debris. This leads us to consider the implications of a potential debris stream. If such a stream exists, could we see larger or closer fragments arriving later? In principle, yes. Debris streams are not uniform. They are characterized by density variations with clumps and gaps resulting from the dynamics of the initial disruption process. Depending on the geometry of this disruption, the leading edge of a stream might be passing through our solar system now, with the main body, potentially containing larger or closer fragments, arriving in the coming years or decades. It's important to clarify, however, that larger or nearer does not necessarily equate to greater danger. Even a 10-kilometer fragment passing at the same distance as the current interstellar object, roughly 270 million kilometers from Earth, would pose no threat. For an impact to be hazardous, the object would need an impact trajectory, an orbit that intersects Earth's path, something that is astronomically improbable for an object on a hyperbolic orbit originating from interstellar space. The current understanding is that the geometry of such trajectories makes a direct collision exceedingly unlikely. Those concerned with planetary defense, experts who focus on tracking and potentially deflecting near-Earth objects, generally concentrate on objects that are gravitationally bound to the Sun. These are the space rocks we can predict, monitor, and if necessary, attempt to mitigate. Interstellar objects, by contrast, are essentially random visitors arriving from outside our solar system, with their paths and timing being largely unpredictable. While we might receive a few weeks or months of warning, depending on an object's brightness and when surveys detect it, deflecting or intercepting a fast-moving interstellar object traveling at 50 or 60 kilometers per second remains beyond our present technological capabilities. It's crucial to emphasize once again that authoritative sources such as AP News, NASA, and the European Space Agency are all clear in their assessments. The interstellar object designated 3I Atlas poses no threat to Earth. Its closest approach in December will be more than 270 million kilometers away, far beyond any impact risk. Even if it fragments or if some as yet undetected component were to change course, the fundamental physics of orbital mechanics make it virtually impossible for such an object to suddenly veer toward Earth's orbit. In short, the risk level is effectively zero. The closest approach of this object to Earth will be more than 250 million kilometers away, a distance so vast that it effectively places us in the realm of cosmic insignificance. Even if this object were to fragment into smaller pieces or if it had unseen companions lurking nearby, the fundamental laws of orbital mechanics impose strict limitations. They prevent any sudden, unexplained course alteration that could suddenly send debris hurtling toward Earth in a collision course. For such a catastrophic scenario, one where debris streams directly toward our planet, the odds are exceedingly slim. Space itself is unimaginably expansive. Earth is a tiny speck within it. To accidentally hit us, this debris would need an incredible stroke of apocalyptic bad luck, a chance so minuscule that it borders on the impossible. So where does the idea of a debris stream headed our way truly stand in scientific and observational terms? It is, importantly, a hypothesis that can be tested, an essential feature that keeps science grounded in empirical inquiry. Over the coming years, if our observations reveal multiple interstellar objects sharing similar parameters, comparable velocities, trajectories, or compositional features, the hypothesis that they originate from a common debris stream would gain increased credibility. Conversely, if each object appears entirely distinct, with no shared characteristics tying them together, this hypothesis would gradually fade into the realm of unlikely speculation. This kind of scientific exploration is inherently provisional. It's perfectly acceptable and even necessary to entertain hypotheses that are currently speculative, provided we clearly label them as such. Importantly, this debris stream scenario does not pose any immediate threat to Earth. Its potential significance lies more in how it could reshape our understanding of the interstellar environment and the dynamic processes occurring across the galaxy. If such streams do exist, they would suggest that our galaxy is far more interconnected and active than previously thought, with catastrophic events in distant star systems casting ripples that propagate across light years and through cosmic time. The universe, in this view, isn't a collection of isolated islands, but a complex web of interactions, violent, scarred, and interconnected. A debris stream passing through our solar system would serve as a stark reminder that we are part of this larger, more tumultuous cosmos. We are not tucked away in a safe bubble. Rather, we are drifting amidst the wreckage of worlds that have long since vanished, their remnants traveling through the dark. However, the strength of science lies in its testability. We should remain vigilant, watching for future interstellar detections that could support or refute this idea. If within the next few years we observe another interstellar object that is rich in carbon dioxide, similar to 3I Atlas, or if its velocity vector resembles that of previous objects, attention should be heightened. Detecting patterns, such as consistent chemical signatures or similar trajectories, would elevate the stream hypothesis from mere speculation to a plausible explanation. Until such evidence emerges, the debris stream remains a possibility, an intriguing idea deserving of further observation but not yet a firm conclusion. This brings us to another crucial aspect, the so-called information gap, the often frustrating delay between when telescopes gather data and when that data becomes publicly available or fully analyzed. This lag fuels suspicions among some that data are being deliberately withheld, giving rise to what can be called the hidden data war, a phenomenon that warrants examination. Let's consider what takes place between the moment a telescope captures photons from an object in space and the moment that information appears in headlines, news reports, or public discussions. This process, while routine, is often painfully slow and meticulous. Initially, the observatory, be it Hubble, JWST, or one of ESA's Mars orbiters, records raw data in the form of photons converted into digital signals. These signals are inherently chaotic and contain artifacts. Cosmic ray hits that produce bright pixels, instrumental noise, calibration drifts, and systematic errors. Before any of this data can be meaningfully interpreted, it must undergo extensive processing. This involves applying calibration frames to correct for detector imperfections, subtracting background signals, correcting distortions caused by Earth's atmosphere or the instrument itself, and converting raw counts into physically meaningful quantities like brightness, spectral flux, or molecular signatures. This processing phase takes time, hours for simple images, days for complex spectra, and potentially weeks if the data is unusual or requires custom analysis pipelines. Only after this rigorous calibration can scientists begin the detailed examination, fitting models to the data, comparing results with theoretical expectations, and preparing reports or publications. This painstaking process is a fundamental part of scientific rigor. It ensures that the results are reliable and reproducible. However, from the perspective of the public or external observers, this delay can seem suspicious, fueling speculation that the data are being deliberately hidden or manipulated. The frustration is compounded when initial reports are cautious or vague, emphasizing that more analysis is needed, or when official releases are slow, sometimes taking weeks or even months before the full dataset or detailed findings are made available. This normal, methodical process is essential to maintain scientific integrity. It prevents premature conclusions. Once the raw data has been meticulously processed and reduced, the dedicated scientific team embarks on a comprehensive analysis. They employ sophisticated models, carefully compare their findings to existing theoretical frameworks, and scrutinize the results for consistency across diverse data sets. This rigorous process involves writing detailed reports, either as scholarly papers or technical memoranda, that document their methodologies, observations, and interpretations. Following this, the work enters the peer review stage, wherein fellow scientists critically examine the draft, verify the methods, and suggest revisions to ensure accuracy and robustness. This cycle of review, revision, and validation can span from several weeks to many months, depending on the complexity of the data and the thoroughness required. If all proceeds smoothly and the data withstands scrutiny, the findings are eventually published in reputable scientific journals or shared as preprints on platforms like ArcCV, making the results accessible to the global research community. Simultaneously, there exists a parallel process of public communication, often termed the public relations track. When the results are particularly compelling or newsworthy, the hosting institution may issue a formal press release to inform the public and media outlets. These press releases are then picked up by science journalists, who craft articles aimed at translating complex findings into accessible language for broader audiences. These articles circulate rapidly through social media channels, comments, and news feeds, gradually disseminating the information to the general public. This entire pipeline, from initial observation to headline, typically unfolds over a span of several weeks to multiple months, and occasionally even longer, depending on the nature of the discovery and the complexity of the data. Importantly, this measured pace is entirely normal and reflects the careful, deliberate nature of scientific inquiry. It ensures accuracy and reliability, fundamental tenets of credible science. However, to an outsider, especially someone eager or anxious about what might be uncovered, this slow process can seem suspicious or even like a cover-up. Questions arise. They observed it weeks ago, so where are the results now? Are they hiding something? The honest answer, in the vast majority of cases, about 99.9%, is that there is nothing to hide. The scientists are simply engaged in routine, meticulous work that doesn't keep pace with the rapid flow of social media and instant news. That said, the contrast between official institutional communication and the often faster, less cautious leaks circulating online creates a perceptual gap. This was vividly demonstrated during the case of Oumuamua, when amateur astronomers and enthusiastic enthusiasts analyzed publicly available astrometry and speculated about its properties days before the official reports surfaced. When the formal press releases finally arrived, they sometimes appeared to contradict or downplay the more sensational interpretations circulating in the unofficial channels. For some, this discrepancy looked like an attempt at damage control, an effort by authorities to prevent panic or to keep certain information under wraps, fueling speculation that They know more than they're telling us. In reality, this difference stems from a fundamental distinction. Early interpretations are often provisional and subject to revision, whereas official statements are based on vetted, confirmed data. Initial assessments, while intriguing, are frequently inaccurate or incomplete. As new data is incorporated and models are refined, the understanding evolves. The institutions involved prioritize accuracy and caution, opting to wait until they can present conclusions with high confidence. This responsible approach, though slower, helps maintain scientific integrity. Meanwhile, the online community, driven by the desire for instant information, shares preliminary insights, sometimes prematurely, trading speed for accuracy. For example, NASA's Goddard Space Flight Center recently published a brief summary article regarding the James Webb Space Telescope's observations of Oumuamua. It highlighted the detection of an unusual carbon dioxide-rich coma and noted the object's asymmetric shape, an act of transparency and openness about initial findings. However, this report was just a summary. The full spectral data, detailed calibrations, and comprehensive observations are still being prepared for peer-reviewed publication. Once released, these data sets will enable other scientists worldwide to access, analyze, and verify the conclusions independently, an essential aspect of the scientific method. Similarly, the European Space Agency has confirmed that both Mars Express and the ExoMars Trace Gas Orbiter will observe Oumuamua during the October 1st to 7th observational window. These agencies will collect additional data which, after processing and validation, will contribute further to the collective understanding. This coordinated multi-instrument approach exemplifies how scientific collaboration and careful communication work hand in hand. Transparency about initial findings, coupled with rigorous validation and open data sharing, form the backbone of credible scientific progress. Social media updates from various institutions and space agencies often provide preliminary information such as observational data, but the processed images and detailed spectra, those definitive results, are typically released later, after thorough reduction and validation. This delay is entirely standard practice in scientific workflows, ensuring accuracy and reliability. However, it also feeds a growing sense of impatience and anxiety among the public and enthusiasts eager for answers. Now let's delve into the realm of media amplification and sensationalism. It's a phenomenon that's become almost ubiquitous in today's information landscape. Sensational stories, whether they champion the idea of an alien mothership approaching Mars or dismiss such notions as baseless, spread with lightning speed. Headlines proclaiming alien mothership approaching Mars can be shared and reshared 1,000,000 times, sparking widespread curiosity and fear. Conversely, headlines suggesting interstellar comet shows unusual chemistry scientists investigating might circulate 10,000 times, capturing attention but often lacking the emotional punch that drives viral content. This stark disparity isn't coincidental. It's rooted deeply in human psychology. We are innately attracted to novelty, especially when it involves threats, real or perceived. Stories that evoke awe, fear, or intrigue activate our emotional centers, prompting shares, comments, and debates. On the other hand, careful, balanced scientific analyses, those that honestly admit, "we don't yet know," fail to trigger the same visceral reactions. As a result, the online ecosystem tends to be dominated by the loudest voices, outlets that sensationalize the alien hypothesis because it drives traffic and engagement, and those that dismiss it outright for similar reasons. The genuine scientific middle ground, an honest acknowledgement of ongoing investigation and uncertainty, gets pushed aside because it's neither sensational enough to attract attention nor conclusive enough to settle debates. Why is it that statements asserting there is no threat are so frequently reiterated? This is an essential part of the responsibility held by agencies like NASA and the European Space Agency. During rare and unexpected events, such as a strange object passing close to Mars, public anxiety naturally rises. People imagine worst-case scenarios from catastrophic impacts to alien invasions. It becomes the agency's duty to provide clear, reassuring communication. "There is no danger to Earth," they declare repeatedly. This isn't mere complacency. It's a deliberate effort to maintain public calm, especially since new audiences are constantly encountering these stories for the first time. Every reassurance helps prevent panic, and re-emphasizing safety is a vital part of their role. Moving on to individual responsibility, specifically evidence literacy, this is a crucial skill that empowers everyone to navigate the flood of information critically. When encountering claims about 3I Atlas, the first step is to ask, where did this come from? Consider the source. Is it a peer-reviewed scientific paper? That's the gold standard, having undergone rigorous scrutiny by experts. Is it a preprint on a platform like Archive? Still valuable, as it indicates scientists are sharing their findings openly and are open to critique. Is it a press release from a reputable institution? Likely trustworthy, although press releases can sometimes simplify or sensationalize results. But if the claim comes from a blog post, a social media tweet, or a YouTube video, caution is warranted. These sources are often less filtered, more prone to speculation, and may lack proper verification. Citations are the backbone of credible science communication. This document, for example, is laden with references, links to NASA pages, European Space Agency releases, preprints, and news reports that form a chain of evidence. If someone makes a bold claim but refuses or neglects to cite a source, that's a red flag. Maybe the claim is accurate, but without verifiable backing, it should be regarded skeptically. It's prudent to hold such claims lightly until confirmed by credible sources. The dynamic nature of scientific discourse is exemplified by the exchanges between researchers like Avi Loeb and critics such as Jason Wright. Disagreement and debate are fundamental to science. They serve as mechanisms for error correction and refinement of ideas. When scientists challenge each other's assumptions and methods, it may look chaotic to outsiders, but that's a sign of a healthy scientific process at work. Disagreement doesn't imply chaos or dysfunction. It indicates active peer review and critical thinking. The friction helps weed out inaccuracies and sharpens understanding. In essence, the scientific enterprise thrives on this friction. It's a feature, not a flaw, that different viewpoints and interpretations are openly debated. Recognizing this helps contextualize the ongoing discussions about objects like 3I Atlas. The process of scientific inquiry, questioning, testing, revising, is the best tool we have to uncover the truth amid uncertainty. When everyone reaches consensus instantly, it's often a sign that no one is truly scrutinizing the details, especially the underlying calculations. The root of this phenomenon isn't necessarily a conspiracy, but a reflection of the current social media landscape, where the demand for quick answers has become relentless. In the scientific realm, telescopes and researchers operate on much longer timelines, weeks, sometimes months, to gather, analyze, and interpret data. This natural delay creates a sense of frustration among the public and enthusiasts alike, which often morphs into wild speculation. Yet rushing science to meet the impatient tick of social media's clock isn't the answer. Fast-tracking results can lead to poor science, misinterpretations, overlooked errors, and faulty conclusions. The real solution is to embrace that uncertainty as an inherent part of the scientific process, and cultivating patience is a virtue vital for genuine understanding. If you wish to stay informed about the evolving story of 3I Atlas in real time, here's a practical approach. Bookmark the Minor Planet Center's dedicated page for 3I Atlas. This is where all new astrometric data, precise measurements of the object's position, are posted as observatories from around the world submit their findings. Regularly check this resource for updates, particularly for preprints or reports with titles containing 3I, Atlas, or Interstellar, which often contain the latest analyses before formal peer review. In addition, it's wise to follow major space agencies such as NASA and ESA, along with the world's leading observatories on social media platforms. However, always remember to look past sensational headlines. Official sources typically communicate measured, cautious updates. The crucial point to bear in mind is that an absence of news does not equate to a cover-up. Sometimes there genuinely is nothing new to report. No breakthroughs, no surprising discoveries, simply because the data collection and analysis are still underway. In that informational vacuum, speculation and conspiracy theories tend to flourish. Part 12 of this ongoing saga is aptly titled The Conspiracy Web, as it encompasses some of the most outlandish claims circulating about 3I Atlas. Now let's brace ourselves. The following cataloging of claims is a collection of the more sensational, often unverified, and in some cases outright false stories circulating online. It's essential to be clear. These are speculative and unsubstantiated. Nonetheless, because many believe them, ignoring these claims won't make them disappear. It's better to shed light on them to understand how they originate and why they persist. First up is the claim of a secret video showing a flyby of 3I Atlas, allegedly captured by one of Mars's orbiters, most often the Mars Reconnaissance Orbiter or Mars Express. The story suggests that these high-resolution images or videos reveal unmistakable geometric structures, panel arrays, or surface markings that look suspiciously artificial. According to the conspiracy narrative, such images are being withheld from the public to prevent panic or to hide evidence that governments have known about extraterrestrial visitors for years. Let's analyze this. To date, no credible or verified images of this kind have been released or leaked. The idea that a definitive, unambiguous image showing alien-like structures could be captured and then suppressed on a planetary scale strains credibility. Space agencies involve thousands of scientists, engineers, and international collaborations, with data shared transparently across borders. Expecting that such an explosive piece of evidence could be secretly hoarded without a single whistleblower or leak is highly implausible. Moreover, the technical limitations of imaging at this distance further undermine the claim. When 3I Atlas makes its closest approach, millions of kilometers away, current high-resolution cameras, even those aboard MRO, would struggle to resolve minute details on such a small, distant, and rapidly moving object, especially one enveloped in a glowing coma. The premise that a clear, detailed video exists and is being deliberately hidden is already questionable. But hypothetically, if MRO did manage to image 3I Atlas and the resulting picture showed something strange, that would indeed be noteworthy. Imagine a faint glint, perhaps a fleeting reflection bouncing off a flat, smooth surface, accompanied by a sudden brightness fluctuation that defies the expected patterns of rotation. What would happen next? The scientific team observing this anomaly would proceed with meticulous analysis. They would scrutinize the data for instrumental artifacts, possible glitches or noise introduced by the sensors, and develop models to account for natural explanations, such as surface irregularities, compositional effects, or observational conditions. If, after thorough investigation, no natural cause could be identified, they would publish their findings. This openness to publishing unexplained data exemplifies the core principle of scientific inquiry. Value lies in uncovering the unknown, not in hiding it. The notion that scientists would deliberately suppress or withhold such intriguing anomalies does not align with how scientific careers are built, on discoveries, transparency, and peer scrutiny, not on cover-ups or secrecy. Moving to a different line of speculation, consider the claims of conspiracy involving military intercept planning. Some suggest that the Department of Defense or other national agencies are actively preparing to intercept 3I Atlas with specialized spacecraft, either to study it closely or to destroy it if deemed a threat. Variations of this theory allege that classified military sensors have detected unusual behaviors, such as rapid movements, acceleration patterns inconsistent with natural objects, and that urgent response measures are already in motion. But let's take a reality check. No official agency has announced any such intercept mission. The closest approach of 3I Atlas to Earth is projected to be around 270 million kilometers in December. Sending a spacecraft across that vast distance, matching velocities of over 50 kilometers per second, would require an enormous amount of fuel and years of preparation, making such a mission impossible on the short time scale discussed. Furthermore, 3I Atlas poses no threat to Earth. It is not on a collision course, nor does it exhibit any behavior warranting a strategic or defensive response. The only plausible reason for a mission to approach it would be out of scientific curiosity. Missions of that nature take years to plan and require significant resources, not something arranged on a whim. As for the so-called fast movers detected by defense sensors, the space surveillance networks operated by the military do track objects in Earth's orbit and beyond, with some data classified due to the sensitivity of their capabilities. However, the notion that they have detected phenomena about 3I Atlas that civilian astronomers have missed is highly unlikely. The trajectory and position of 3I Atlas have been monitored by dozens of observatories worldwide, with measurements of high precision. If it were performing maneuvers, those would be evident in the astrometric data available to anyone analyzing the orbital mechanics. It's simply not possible to hide such movements from the rigorous calculations of celestial mechanics. Now let's explore a different facet of the cyber-sleuthing community's activity. Various online forums, Discord channels, and UFO-focused subreddits have been abuzz with analysis of supposed leaked frames, blurry images, or video snippets claiming to show detailed views of 3I Atlas. Some assert they see geometric patterns, regular shapes, or structures that seem unlikely to be natural, while others point to brightness variations that resemble running lights or energy signatures. These images circulate rapidly, often accompanied by claims of extraordinary discoveries. But here's the challenge. Many of these are based on low-resolution images or pixelated footage. Our brains are wired to find patterns even where none exist. This phenomenon, known as pareidolia, causes us to perceive meaningful images, faces in clouds, figures in ink blots, or spacecraft in noisy pixel data, simply because we are predisposed to seek familiar shapes and significance. In other words, blurry images or ambiguous data are easily filled in by our minds with familiar patterns, leading to subjective interpretations rather than objective evidence. Without comprehensive metadata, calibration details, and source verification, any image or data, no matter how striking, loses its value as credible evidence. Such images could easily be misclassified solar system objects, mere instrumental anomalies, or even outright fabrications. Unless the source can be definitively traced back to a specific observatory, accompanied by documented observation parameters, they should be regarded solely as entertainment, not as scientific data. Both the Daily Beast and The Guardian have published articles concerning 3I Atlas, illustrating how narratives tend to diverge based on framing. The Daily Beast has embraced the speculative angle, emphasizing the strangeness and quoting Low prominently, feeding into the what if it's an alien storyline. Conversely, The Guardian, especially in pieces quoting mainstream astronomers, has emphasized the natural comet-based explanation, cautioning against sensationalist narratives. Both outlets are legitimate, but they serve different audiences and craft their stories to resonate with their readership's expectations. This isn't a coordinated effort to spread disinformation, rather it's journalistic response to market pressures. The Daily Beast understands that its audience is captivated by the possibility of alien technology, by the what-if scenarios involving extraterrestrial origins, while The Guardian's science coverage appeals to those seeking a more grounded scientific perspective. Both perspectives coexist within the broader public discourse, yet neither offers a complete or definitive picture on its own. This leads us to a fundamental question. If someone truly wanted to conceal a breakthrough discovery, could they succeed? Suppose JWST detected unmistakable technosignatures in 3I Atlas's spectrum, say, a narrow emission line at a frequency that matches human-made signals but cannot be naturally produced, or thermal emissions indicating active power generation. Could NASA or any other agency suppress that information? The short answer is unlikely and not for long. Here's why. JWST's data undergoes multiple layers of processing through various pipelines overseen by the Space Telescope Science Institute, with multiple co-investigators and scientists having access to the raw and processed data. It's archived systematically, and after an initial proprietary period, the data becomes publicly accessible. To hide such a discovery, hundreds of scientists and engineers across numerous institutions would need to be complicit and remain silent, an almost impossible feat given human nature. Scientists are notoriously poor at keeping secrets, especially exciting ones, because the incentive structure heavily favors publication and recognition. Publishing a paper claiming we've found evidence of alien technology would be a career-defining achievement. Conversely, agreeing to silence that discovery indefinitely would serve no tangible benefit. What would they gain? Perhaps a pat on the back from shadowy agencies that may not even exist. Furthermore, 3I Atlas has been observed by multiple independent facilities, spacecraft orbiting Mars, ground-based telescopes in Chile, Hawaii, Spain, and Arizona, as well as hundreds of amateur astronomers with backyard telescopes. The Minor Planet Center has received thousands of position measurements from numerous contributors worldwide. If NASA or any other institution attempted to suppress anomalous findings, someone else, an independent scientist or observatory, would inevitably notice and publish the data. Controlling such a vast network of observation channels is effectively impossible. Even if, for the sake of argument, all major institutions conspired to keep a discovery secret, the scale of that conspiracy would be staggering, requiring coordination across multiple countries, dozens of organizations, and thousands of individuals. Conspiracy theories of that magnitude tend to crumble under their own weight, as leaks and whistleblowers are almost inevitable in such extensive clandestine efforts. Individuals speak. Secrets find their way into the open, and conscience often compels someone to break the silence. The larger the secret, the more fleeting its existence. Its half-life becomes surprisingly brief. To make progress, one must identify a tangible, testable indicator, what scientists call a falsifiable hook, that can conclusively support or refute a particular hypothesis. Suppose a clear, high-resolution fly-through video existed, capturing something truly extraordinary, an unmistakable artifact, a structural signature, or a technological signature. When would we expect such footage to surface publicly? Looking back at previous timelines for Mars orbiter data, preliminary findings typically emerge within a matter of weeks, while comprehensive datasets often take several months to fully analyze and publish. If, by the months of November or December, no images or videos have been released, no matter how much time passes, it strongly suggests one of two possibilities. Either these images simply do not exist, or they exist but do not reveal anything unexpected or groundbreaking. Both scenarios tend to weaken the conspiracy narrative. This is where psychological awareness becomes crucial. Our minds are naturally inclined to seek patterns and fill gaps in incomplete information, an evolutionary survival trait that has kept humanity alive. In ancestral times, assuming a rustle in the grass was a predator was often the right call. It kept us alert and safe. But in today's information age, that same mechanism can lead us astray, making us susceptible to conspiracy theories. Every missing piece of data transforms into a potential cover-up. Every delay raises suspicion, and every official statement, no matter how measured, can sound like deliberate obfuscation. Statements like, "There's nothing to worry about," can be perceived as exactly what one would expect if there were something to hide. The antidote to this cognitive trap involves two key strategies. First, self-awareness. Recognize when you're constructing elaborate explanations to justify the absence of information. When this happens, pause and question whether the simplest explanation, namely that data simply takes time to process, is sufficient. Second, demand evidence that matches the level of the claim. Extraordinary assertions such as governments are concealing proof of extraterrestrial life necessitate extraordinary evidence. A blurry image or a mere hunch does not meet that threshold. So where does this web of conspiracy theories leave us? Most claims are unfounded, rooted in misunderstandings of how space agencies operate. Some may even be deliberate fabrications crafted to generate clicks, stir controversy, or sell merchandise. But their persistence isn't due to widespread stupidity. Instead, it stems from the confusing, often opaque landscape of space data. Public timelines are slow, and the allure of discovering something extraordinary fuels our desire for revelation. We yearn for the universe to be more than a collection of rocks and gas. We want to believe in the possibility of alien life. This longing makes us vulnerable to narratives that promise the unveiling of secrets. Yet when the dust settles, when the Mars data is thoroughly analyzed and released and additional observations are made during perihelion, most of these conspiracy theories will quietly fade into the background. The true enthusiasts will shift their focus to the next enigma, while skeptics may say, "I told you so." Meanwhile, scientists will continue their normal course, collecting data, testing hypotheses, refining models, and revising theories based on new evidence. This process might lack the sensationalism of a dramatic cover-up, but it is the true engine of scientific progress. As the debate continues over the true nature of this mysterious object, it's worthwhile to explore the strongest arguments from both perspectives. Let's consider the reactions from philosophers and physicists. Analyzing the diversity within the scientific community itself, it's important to recognize that the community isn't a single unified voice. When you walk into a room of astronomers asked about the nature of 3I Atlas, expect a spectrum of responses. Some will confidently assert that it is a natural object, a comet or asteroid, based on the current evidence. Others will advocate for a more cautious stance, emphasizing the importance of maintaining an open mind until definitive proof emerges. This disagreement isn't a flaw. It's the essence of scientific inquiry, where ideas compete and evidence ultimately determines the consensus. Certainly. Here's a polished, expanded version of the passage, preserving its core ideas while enriching the language and flow. When discussing the nature of 3I Atlas, you'll encounter a spectrum of opinions ranging from outright certainty, "It's undeniably a comet," to a more cautious stance, "Let's keep our options open until we have concrete, definitive proof." This divergence in perspective isn't a flaw or a sign of weakness. Rather, it exemplifies the fundamental way science advances. Ideas are always in competition, and evidence serves as the ultimate arbiter. To understand the current landscape, let's map out the prominent camps. First, there is the empiricist faction, those scientists who follow in the footsteps of experts like David Jewett and Karen Meech. These researchers have dedicated their careers to studying comets and asteroids, developing an intimate understanding of the natural populations and their behaviors. Their approach is straightforward. Prioritize the data, assume the object is natural unless proven otherwise. They examine the JWST's spectroscopy, which reveals the presence of water, carbon dioxide, carbon monoxide, and carbon sulfide, all of which are well-known natural volatile compounds. Based on this, they conclude, this is a comet. They observe the asymmetrical shape of the coma and interpret it as jetting activity, behavior that is quite common among natural comets. They note that the weak non-gravitational acceleration observed could be explained by balanced jets or a high-mass object, scenarios that we have documented before in our solar system. For these scientists, the bar for claiming an object is artificial is set very high, and rightly so. History offers cautionary tales. In 1967, pulsars were discovered, their signals so consistent and regular that Jocelyn Bell and Anthony Hewish joked about little green men. Only later were they understood to be rotating neutron stars, a natural but exotic phenomenon. Similarly, the famous WOW signal of 1977 appeared as a narrow-band transmission that matched the kind of signal SETI was searching for. Yet, it was never repeated or conclusively explained, remaining a curious anomaly rather than proof of extraterrestrial intelligence. Even mysterious phenomena like fast radio bursts, once thought to be inexplicable, were eventually attributed to natural astrophysical objects such as magnetars and other exotic stellar remnants. The pattern is consistent. Something appears strange, initial speculation arises, but natural explanations invariably emerge, transforming these anomalies into new categories of natural phenomena. The empiricist stance, therefore, is one of restraint and thoroughness. They advocate, let's not jump to conclusions about artificiality until we have exhausted every plausible natural explanation. And in the case of 3I Atlas, this approach seems to fit well. The chemistry, though unusual, can be explained within known frameworks. The size and mass estimates, while uncertain, remain within plausible ranges. Its hyperbolic trajectory confirms its interstellar origin, and so far there is no evidence of maneuvering or artificial control. From this perspective, the case for it being a natural comet appears sufficient, at least for now. On the other side of the debate is the pluralist or possibilist camp, with voices like Avi Loeb leading the charge. Their position is more nuanced than the headlines suggest. They are not outright claiming that 3I Atlas is definitively artificial. Rather, they argue that the presence of anomalies, even if each could be explained by natural mechanisms, collectively raise enough questions to warrant serious consideration of alternative hypotheses. This camp emphasizes that the reluctance to even discuss extraterrestrial artifacts stems from a stigma, a bias that discourages open-minded inquiry. Loeb's Loeb scale, a tool he devised as an attention allocator, exemplifies this approach. On this scale, a score of 4 out of 10 indicates that the object is weird enough to merit additional observational resources to rule out the possibility of artificial origin. It's not a statement of probable alien technology, but rather a triage, identifying objects that deserve closer scrutiny because the anomalies are significant enough to justify further investigation. In essence, the Loeb scale functions as a prioritization system. When an object scores 4 out of 10, it signals, "This is intriguing. Let's allocate more scientific attention to it." The goal isn't to jump to conclusions, but to systematically evaluate and rule out all plausible natural explanations before considering the extraordinary hypothesis of extraterrestrial origin. In this way, the pluralist approach advocates for a balanced, open-minded scientific process, one that recognizes the value of investigating anomalies without prematurely dismissing unconventional possibilities. It encourages a rigorous, evidence-based triage, an essential framework in a field where the universe continually surprises us. The central argument here underscores a crucial point. If we continually refrain from actively seeking signatures of artificiality because we are predisposed to see everything as natural, we risk overlooking genuine extraterrestrial technology, even if it exists right before our eyes. This presents a profound philosophical dilemma about the standards of evidence in astronomy. Essentially, what level of proof should we require before accepting an extraordinary claim? In the realm of astronomy, absolute certainty is an elusive goal. We face inherent limitations. We cannot directly manipulate or recreate these distant objects within a laboratory setting, nor can we perform controlled experiments on them. Our understanding is derived solely from the light they emit or reflect, the gravitational influences they exert or experience, and the patterns we observe in their trajectories. All of these inferences are probabilistic by nature, not definitive. This raises a fundamental question. At what point should we consider an explanation credible enough to warrant serious scientific attention? Most scientists tend to adopt a very high threshold for considering an object possibly artificial, often around 99% confidence or higher. This means that unless the evidence overwhelmingly points to an artificial origin, they remain cautious. Conversely, some may accept a lower confidence level, 60 to 70%, particularly when the evidence is suggestive but not conclusive. This divergence reflects deep-rooted differences in how scientists update their priors, basic assumptions about what is likely, using Bayesian reasoning. The debate over where to set this threshold is essentially a disagreement about prior beliefs and risk tolerance. Neither approach is inherently wrong. Both are different risk assessments. The empiricists prioritize avoiding false positives, meaning they are cautious about prematurely claiming extraterrestrial origins, wary of mistaking a natural object for an alien artifact. Their goal is to prevent the kind of scientific pitfalls that lead to false alarms. On the other hand, the pluralists or more open-minded researchers emphasize the importance of not dismissing anomalies too quickly, avoiding false negatives, because doing so might cause us to overlook genuinely significant discoveries simply because they don't fit current expectations. This tension is compounded by what can be described as institutional fatigue. Many researchers, having been asked the same questions repeatedly, whether about unusual comets, asteroids, or signals, become weary of the endless cycle of natural explanations. These phenomena are often dismissed as benign or explainable, and the question, could this be alien, becomes a distraction rather than a serious inquiry. Every time an object exhibits strange behavior, it is quickly rationalized away as a natural phenomenon, and the media and public discourse amplify the narrative that we're overreacting or chasing ghosts. This creates a kind of noise, public fascination, and media sensationalism that hampers the progress of genuine science. Telescopes and observatories are inundated with observation requests, diverting valuable time and resources. Communication channels clog with questions from journalists and amateurs, and scientists spend disproportionate effort on damage control rather than advancing understanding. It's a perverse incentive. The more one publicly entertains the possibility of alien life, the more attention and scrutiny one attracts, which can hinder objective analysis. Consequently, many scientists choose to minimize engagement with the extraterrestrial hypothesis, focusing instead on natural models. This isn't necessarily a cover-up, it's a matter of time management and prioritization. Yet this strategy can be misinterpreted as dismissiveness or dogmatism, fueling conspiracy theories that claim mainstream science is hiding the truth. Historical analogues remind us of how easily perceptions can be misled by optical illusions or low-resolution data. In the late 1800s and early 1900s, some astronomers claimed to see linear features on Mars that resembled artificial canals, later revealed to be optical illusions and artifacts of poor resolution. Similarly, pulsars were initially thought to be potential beacons or signals from intelligent civilizations, but it was eventually understood they are rapidly rotating neutron stars, natural phenomena that appeared strange but had natural explanations. More recently, in 2020, an object labeled 20-20 CSO was initially mistaken for an asteroid but was later identified as a human-made rocket booster from the 1960s, with orbital dynamics confirming its artificial origin after weeks of analysis. These historical episodes serve as humbling lessons. Nature often surprises us with phenomena that seem unnatural or artificial until we better understand them. Sometimes what appears to be a sign of alien technology is simply a natural process or a known object that we have yet to fully catalog. Such analogues remind us to approach anomalies with cautious curiosity, recognizing the limits of our current knowledge and the importance of rigorous analysis before jumping to extraordinary conclusions. Occasionally, very rarely, what appears to be strange or inexplicable can turn out to have a human origin, as indeed was the case with the object known as 2020 CSO. While the leap from a human-made artifact to an extraterrestrial one is undeniably vast, encompassing differences in origin, purpose, and technology, it is not beyond the realm of possibility and principle. However, with current confirmed history, there has been no such instance of an object turning out to be alien-made, which statistically renders the prior probability remarkably low. Yet it's important to recognize that zero occurrences in a small sample size do not categorically rule out the possibility. It simply means it remains highly improbable based on what we know so far. This line of reasoning naturally leads to significant policy considerations. If the object designated as 3I Atlas were to be confirmed as an artificial construct, regardless of whether it is benign or potentially threatening, it would fundamentally challenge existing frameworks of space law, traffic management, and protocols for contact. The Outer Space Treaty, signed in 1967, currently governs activities in space and designates celestial bodies as the shared heritage of humankind. It was drafted with the assumption that all spacefaring objects originate from and are controlled by human or national space agencies. But if we were to find an object with clear signs of extraterrestrial origin, capable of performing functions beyond natural processes, questions about jurisdiction immediately arise. Who would have authority over such an object? Who would decide whether to attempt communication? And what are the potential risks, both scientific and geopolitical, of actively trying to signal or engage with it? In the realm of SETI, search for extraterrestrial intelligence, there exist established post-detection protocols that advocate for international consultation before responding to any detected signals or objects. These procedures are designed to prevent unilateral actions that could escalate tensions or lead to misunderstandings. However, they are voluntary and have yet to be tested in real-world scenarios involving physical objects, as opposed to electromagnetic signals. If 3I Atlas were, in fact, an active probe collecting data about our solar system, the question becomes, should we try to communicate? Should we attempt to wave at it with lasers, send radio messages, or instead adopt a cautious stance of silent observation to avoid drawing unnecessary attention? These are not trivial questions, and consensus on their answers remains elusive within the scientific and policy communities. A critical lesson from science communication is the importance of managing public curiosity and wonder without overstating certainty or creating unwarranted fears. The public has a right to accurate, transparent information. They deserve to know when an object or phenomenon is genuinely unusual, and when it might merely be a natural occurrence that's been sensationalized. Equally, they should be encouraged to share in the excitement of discovery and participate in the collective effort to understand our universe. Walking this fine line between transparency and alarmism is inherently challenging. Overemphasizing the alien hypothesis risks fueling speculation and conspiracy theories, while downplaying legitimate anomalies can seem evasive and dismissive. The best approach, therefore, is likely to embrace transparency about what is known and what remains uncertain. It involves openly communicating the current evidence, the questions scientists are asking, and the steps being taken to gather more data. Explaining why some scientists interpret the data one way and others another helps foster public trust and understanding. Presently, most experts agree that the prevailing hypothesis for 3I Atlas is that it is a CO2-rich interstellar comet, but they remain open to surprises. Continuous observation and analysis are essential. If genuine anomalies emerge, they should be thoroughly investigated without prejudice, allowing the evidence to guide conclusions rather than preconceived notions. Regarding the ongoing debate over how to rate the object's potential artificial origin, the record is straightforward. Initially, in early August, Avi Low and colleagues provided an estimate suggesting a 6 out of 10 on their Loeb scale, indicating a moderate to high likelihood of technological origin. As more data, particularly from the James Webb Space Telescope, became available, Low revised that estimate downward to 4 out of 10, reflecting increased confidence in a natural explanation. This adjustment exemplifies how the framework is designed to work. Scores should evolve in tandem with the evidence, becoming more refined over time. As we gather additional information, such as continued comet-like behavior through perihelion, stable spectral signatures, and lack of signs of maneuvering, the confidence level will likely decrease further, reinforcing the natural origin hypothesis. Conversely, if unexpected behaviors or technological signatures are detected, the score could rise again. The framework is inherently provisional, iterative, and rooted in the latest data, emphasizing that our assessments are always subject to revision as new evidence emerges. Certainly. Here's a polished, expanded version of your text, maintaining the core ideas but enriching the flow and detail. Whether one concurs with the precise numerical estimates or not is ultimately secondary to a fundamental principle. Our confidence in any hypothesis should evolve and become more refined as new evidence is gathered. In essence, scientific judgment must be dynamic, continuously updating with each fresh piece of data. This principle leaves us at a crossroads, with philosophers and physicists divided in their interpretations. The majority of experts lean toward the view that this object is a natural comet, an exotic interstellar visitor shaped by cosmic processes. A smaller, more cautious minority advocates for heightened alertness, pondering whether we might be witnessing something more extraordinary, perhaps artificial or engineered. So far, the weight of evidence tilts toward the conventional, but the door to alternative possibilities remains slightly ajar. The upcoming observations from tonight's encounter with Mars could very well provide critical data, either reinforcing the natural origin theory or nudging us toward a paradigm shift. The question now is, what exactly did we receive back from this cosmic flyby? This is part 14 of our ongoing story, the results from the Mars encounter. Let's begin by clarifying what we are aiming to detect and what realistic expectations should guide our interpretation. Because as you listen, the spacecraft instruments in orbit around Mars are either already collecting or about to collect data. And by the time you hear this, the initial findings will be processed, but not yet fully released to the public. This segment serves both as a brief summary of what we might see, and as a preview of which signals or features to focus on when the detailed data finally becomes available. The first key indicator to watch for is the shape and behavior of the comet's coma, specifically how its asymmetry correlates with the Sun's position. The James Webb Space Telescope observed a markedly uneven coma back in August, revealing that the outgassing isn't uniform across the surface. Instead, there are distinct jets, preferred regions where gases and dust are venting more vigorously. If the comet is primarily heated by solar radiation, then as it journeys through its orbit, the changing angle between the Sun, the comet, and our vantage point should cause the coma's shape to evolve in predictable ways. Observations from the orbiters around Mars, which view the object from a different perspective than Earth-based telescopes, can test whether the asymmetry behaves as the thermal models suggest. If the coma's shape and the jet's directions align with heating patterns predicted by our understanding of sublimation and solar illumination, that would strongly support the natural comet hypothesis. Conversely, if the jets are pointing in directions that defy the expected correlation with sunlight, perhaps oriented oddly or inconsistent with the solar heating geometry, that would constitute an anomaly worth further investigation. Next, we consider the presence of collimated jets or outbursts, features that are hallmark behaviors of many comets in our own solar system. Collimated jets are narrow, well-defined streams of gas and dust that emerge from specific vents or fractures on the nucleus, as opposed to a broad, diffuse outflow. Detecting such focused streams indicates that the nucleus likely contains structural features such as fractures, vents, or fissures funneling the material outward. Outbursts, on the other hand, are sudden, brief surges in activity, often triggered when pockets of volatile materials beneath the surface suddenly breach the crust, releasing a burst of gas and dust. These phenomena are well documented in solar system comets, providing clues about their internal structure and volatile distribution. If similar features are observed in 3I Atlas, it would lend further weight to the idea that we are witnessing a natural icy body behaving in predictable comet-like ways. On the other hand, the absence of outbursts or collimated jets, while not necessarily alarming, is worth noting. It might simply suggest a different internal composition or a more dormant phase, but it remains a piece of the puzzle. Third, attention should be paid to the thermal profile of the object, specifically how its infrared emissions compare to expectations. Every object in space emits thermal radiation, which depends on how much sunlight it absorbs and how efficiently it re-radiates that heat into space. For a typical comet, the dominant source of thermal emission generally comes from dust grains in the coma, which heat up as they absorb sunlight. If infrared observations show a thermal profile consistent with dust at the comet's current distance from the Sun, that would align well with a natural sublimation-driven activity. However, if there are unexpected hotspots or colder regions that don't match the predicted thermal models, say areas that appear unusually warm or cold, this could be significant. Such irregularities might indicate pockets of exposed ice versus dust-covered surfaces, or perhaps localized activity driven by internal processes or compositional heterogeneity. In sum, the detailed thermal mapping will provide vital clues about the physical state and surface properties of 3I Atlas. A natural object would likely exhibit a thermal pattern consistent with. It is essential to approach this with meticulous care by constructing detailed models. When ESA or NASA eventually release preliminary findings, certain key indicators in their official statements can guide our interpretation. First, pay close attention to their language. Are they confidently categorizing the object as a comet, or are they employing cautious phrasing such as consistent with cometary activity, or no anomalies detected? Such wording suggests they're observing behavior that aligns with natural expectations and aren't detecting anything particularly unusual. Conversely, phrases like unusual features or further analysis required might hint at data that could challenge the natural explanation, indicating the presence of anomalies worth investigating further. Second, scrutinize the specifics of their measurements. Did they determine a rotation period? Are there spectral lines detected beyond what JWST observed previously? Have they noted any changes in the activity level of the object over time or as it approached perihelion? These details can reveal whether the object is behaving as a typical comet or exhibiting signs of something more exotic. Third, consider how they compare the current observations to previous baseline data, especially JWST's observations from August 6th. Are they reporting that the ratio of carbon dioxide to water remains steady or has it shifted? An increase in water relative to CO2 would bolster the radiation crust model, supporting the idea that deeper water-rich layers are now being exposed and outgassing as the object heats. On the other hand, if the ratio remains stubbornly CO2-dominated, it points toward an intrinsic compositional anomaly. Perhaps an object formed under unusual conditions or with a fundamentally different makeup. Additionally, check whether they mention the presence of fragile molecules such as carbonyl sulfide, OCS. Since OCS is easily broken down by ultraviolet radiation, its persistence would indicate that the comet's surface or nucleus has some shielding, or that the activity patterns are more complex than simple sublimation models suggest. Observe whether the constraint on non-gravitational acceleration has become more precise after the Mars encounter. As more data accumulates over time, the orbit fitting improves and the limits on the object's acceleration tighten. If the measured acceleration remains weak but now with higher confidence, it lends support to the heavy nucleus hypothesis, implying the object is more massive and less affected by outgassing forces. Conversely, if the acceleration suddenly increases or shows a direction that can't be explained solely by outgassing, especially if it contradicts earlier models, this could be a cause for concern and may point toward artificial maneuvering or other unnatural influences. Let's assess these hypotheses with an honest scoreboard. If the Mars data shows no surprises, if the comet's behavior is consistent with natural comet-like activity, and the spectral signatures remain rich in volatiles without any signs of technologically derived markers, then the evidence continues to favor the traditional comet explanation. In such a case, the probability of an artifact diminishes, perhaps from a tentative 4 out of 10 down to 2 or 1 out of 10. The debris field hypothesis, which posits that this object might be a fragment from a larger catastrophic event elsewhere in the galaxy, is inherently more challenging to test with a single observation. We would need to identify companions or detect signs of unusual fragmentation, neither of which seems likely based solely on this encounter. However, any surprises, such as a dust grain-sized distribution that deviates from typical comets, or the detection of unexpected emission lines or molecules, would warrant a deeper investigation. An abrupt brightness spike, a sudden increase in reflected light that doesn't align with known natural processes might represent an outburst or, even more intriguingly, something stranger. Communication dynamics also matter. How quickly do teams publish their findings? If results emerge within a week or two, it could indicate that the data was straightforward to analyze or that a surprising, possibly groundbreaking feature was identified, prompting rapid dissemination. Longer delays, over several weeks or months, are typical, reflecting the careful process of calibration, analysis, peer review, and verification. Overall, paying close attention to wording, measurement details, comparative analyses, and publication timing will help us interpret the evolving picture of this mysterious visitor with clarity and rigor. If the analysis takes several months, that is considered standard practice in scientific research. However, it tends to be less thrilling for those eager for immediate answers. During this period, the scientific community anticipates presentations at upcoming conferences, which serve as vital forums for sharing preliminary findings. The American Astronomical Society holds regular meetings every few months, providing opportunities for researchers to discuss recent discoveries. Similarly, the European Astronomical Society hosts its own conferences, with the Division for Planetary Sciences of the American Astronomical Society playing a particularly significant role in this context. If researchers choose to present initial results regarding the interstellar object known as 3I Atlas at these venues prior to formal publication, their abstracts and slide decks are often shared publicly, either through conference proceedings, preprints, or institutional channels. This process underscores the importance of distinguishing between rumors and verified data. For example, if someone claims that the European Space Agency detected a metallic reflection from the object, the pertinent question is, where is the supporting data? If the claim isn't documented on ESA's official website, isn't available in a preprint repository, and hasn't been corroborated by multiple independent sources, it should be regarded as a rumor rather than a confirmed fact. Rumors may originate from misunderstandings, deliberate misinformation, or premature leaks of provisional data that are subject to revision upon further analysis. Patience and reliance on official channels and peer-reviewed publications are essential before accepting such claims as factual. This caution is especially critical when dealing with extraordinary assertions. For instance, if a puzzling glint or a sudden reflectance spike, lasting just a few seconds or minutes, is detected that does not fit conventional models of thermal emission or rotation, what might that signify? The first step is to systematically rule out instrumental artifacts. Bright pixels caused by cosmic ray hits can mimic transient signals, and scattered sunlight from the Sun, Mars, or the spacecraft itself might produce fleeting reflections. Next, natural explanations must be considered. Ice grains within the comet's coma can produce specular reflections if oriented correctly, and tumbling fragments might catch sunlight at specific angles, creating brief flashes. Only after these natural causes are thoroughly excluded should one consider artificial scenarios. For example, if the reflection pattern cannot be explained by known natural processes, a hypothesis involving a flat reflective surface, potentially a manufactured panel, rotating into view might be proposed. Comparing the observed light curve to the predicted pattern for such a surface can provide critical insights. If the observed glint aligns with the model, it warrants deeper investigation. However, if it does not, natural explanations regain plausibility. Confirmation of artificial origin would require that such effects are repeatable and consistent with a specific rotation period. Multiple glints occurring at regular intervals would suggest a structured, possibly engineered surface. Patterns like these are the starting point for developing hypotheses about the object's nature. But let's be pragmatic. The most probable outcome of tonight's Mars flyby is that the data will reaffirm what current observations already strongly suggest: that 3I Atlas is a large CO2-rich interstellar comet. It's active, exhibits unusual chemistry, and provides valuable scientific insight. Importantly, it is not a mothership or a fragment from some distant doomsday debris stream heading toward Earth. Instead, it appears to be a natural object exhibiting exotic but explainable behavior. Perhaps a reminder of how diverse comet formation can be in other star systems. In the weeks ahead, additional data will help clarify its true nature, and with each new observation, the scientific narrative will evolve. So what lies beyond tonight's encounter? The next chapter, Part 15, looks to the future sky, where the possibility of a fourth interstellar visitor awaits. Yet let's anchor ourselves in what we can confidently affirm. 3I Atlas is undeniably interstellar. Its hyperbolic orbit, its velocity, and the astrometric measurements from dozens of observatories worldwide all confirm that this object originated outside our solar system. Rest assured, it poses no threat to Earth. In December, it will make its closest approach about 600 times farther than the distance to our moon, at roughly 270 million kilometers away. This vast separation ensures that, regardless of its size or composition, it remains harmless from a planetary defense perspective. Even if all the most cautious, pessimistic assumptions about its size and composition prove correct, there is no immediate threat of collision. The closest approach of this object to the Sun, known as perihelion, will occur around October the 30th in the year 2025, at a distance roughly equivalent to 1.4 astronomical units. This upcoming perihelion represents our most critical observational window, an invaluable opportunity to glean answers about its activity levels and chemical makeup. During this period, astronomers worldwide will be scrutinizing the object intensively, hoping to resolve lingering questions that have persisted since its discovery. Reflecting on what we have learned so far, the most significant realization is that interstellar objects rich in carbon dioxide do indeed exist. Prior to the arrival of 3I Atlas, our catalog contained only one confirmed interstellar comet, Borisov, an object that was notably water-rich and bore a striking resemblance to typical comets within our own solar system, merely passing through from beyond. Now, with 3I Atlas, we understand that the population of interstellar visitors encompasses a broader chemical diversity than previously thought, including compositions that are not commonly observed among our native cometary bodies. This is not entirely surprising when considering that different star systems have distinct formation environments, with varying disk temperatures, chemical abundances, and evolutionary histories. For example, a comet that originated around an M dwarf, a red dwarf star, would have experienced different thermal regimes compared to one formed around our Sun, a G-type star. Such variations naturally lead to a wide range of chemical compositions among interstellar objects. While we should expect such diversity, the reality of observing it is another matter entirely. Expectation alone does not guarantee detection. Our current observations are just beginning to reveal the extent of this variability. 3I Atlas provides us with our first confirmed data point that highlights this diversity, opening the door to deeper understanding. A second important lesson from this encounter is that activity, manifested as outgassing and coma formation, does not necessarily translate to a proportionally large non-gravitational acceleration. The common assumption has been that when a comet's coma is visible, we should observe a corresponding significant push on its trajectory due to the reaction force of outgassing. However, 3I Atlas demonstrates that this is not always the case. It is possible for jets to be balanced or for the object's mass to be sufficiently high, perhaps both factors at play, that the net acceleration remains minimal despite ongoing activity. This insight is crucial for our modeling efforts and for predicting future trajectories with precision. Looking ahead, the next major observational milestone is perihelion on October the 30th. During this period, solar heating will reach its maximum, and if the object is prone to outbursts or increased activity, this is when they are most likely to occur. Should the CO2 to H2O ratio shift significantly, a sign of changing outgassing dynamics, perihelion presents the best chance for detection. Earth-based telescopes will be meticulously monitoring the object, collecting data that may confirm or refine current models. Space telescopes, if granted observation time, could provide complementary insights, offering a different vantage point in space that could reveal details impossible to discern from the ground. This perihelion passage is arguably our last and best opportunity to thoroughly characterize this visitor before it begins its journey back into the depths of space. Besides Earth-based instruments, there are other platforms in space that might contribute. NASA's Psyche mission, launched in 2023 and currently en route to the metallic asteroid Psyche, could potentially observe 3I Atlas from a different perspective within the solar system. Similarly, the European Space Agency's JUICE mission, also discussed earlier, might provide long baseline observations as it travels toward Jupiter. While these missions were not launched specifically to study interstellar objects, their trajectories and instruments could be suitable for opportunistic observations if the scientific case proves compelling enough. It is important to note that such observations are not guaranteed. Mission teams prioritize their primary objectives, and interstellar visitors are considered targets of opportunity, meaning that dedicated observations depend on the strength of the scientific case and the available scheduling windows. Nonetheless, as tracking continues over the coming months, the long-term orbital dynamics will become clearer. Each additional month of observation improves the precision of the trajectory estimate, reducing uncertainties and enabling detection of even the most subtle non-gravitational forces acting on the object. This ongoing effort will refine our understanding of its motion, composition, and possible internal structure, providing critical data for future analysis. Should there be any subtle accelerations or minute maneuvers that current observational data cannot definitively resolve, ongoing and meticulous tracking will eventually uncover them or, conversely, confirm their absence altogether. This process of continuous monitoring is poised to revolutionize our understanding, especially with the imminent arrival of the Vera Rubin Observatory. Equipped with a massive 8.4-meter mirror and an expansive field of view, this state-of-the-art facility will systematically survey the entire sky visible from Earth with unprecedented frequency. Its efficiency surpasses that of existing telescopes, enabling it to detect transient phenomena and swiftly moving objects with remarkable precision and volume. Predictions suggest that Rubin could discover approximately one interstellar object each year, with the potential for even more frequent detections as technology advances. Over the span of a decade, this means we might compile a comprehensive catalog of between 30 and 50 confirmed interstellar visitors, objects originating beyond our solar system. Such a dataset would transform statistical analyses from mere speculation into solid science, allowing us to chart the distribution of sizes, identify compositional trends, and map velocity vectors across a broad population of these celestial wanderers. Armed with this wealth of data, scientists will be able to determine whether objects like 3I Atlas are exceptional anomalies or representative of a common class of interstellar bodies. We will clarify whether large CO2-rich comets are rare flukes, or if they are more prevalent than previously thought, perhaps just the brightest among a vast faint population. We may also discover whether such large objects are truly outliers, or if our current detections merely reflect a selection bias toward the most luminous or active objects, which are easier to spot. Rubin's observational prowess will extend further, reaching down to smaller objects that currently elude detection. Presently, our surveys favor larger or more active interstellar objects because their brightness makes them easier to detect against the cosmic background. However, with Rubin's heightened sensitivity, the landscape of interstellar object detection will shift dramatically. We will start to see smaller bodies down to 100 meters in diameter, roughly the size of a modest boulder, and even pebbles as small as 10 meters across. If the distribution of these small objects aligns with the predictions made by natural models of ejection from planetary systems, that will reinforce our understanding of the processes shaping our galaxy's interstellar population. But if instead the data reveal unforeseen patterns, such as unexpected clustering gaps or anomalies, this will open a new chapter of scientific inquiry, raising fresh questions about the origins and nature of these objects. Now let us evaluate the current standing of various hypotheses following tonight's perihelion observation. The comet hypothesis, supported by the most substantial body of evidence, remains the most plausible. It accounts for the detected natural volatiles, such as carbon dioxide and water, and aligns with the observed symmetry and behavior of the coma. Although the non-gravitational acceleration is weak, it is consistent with models of balanced jet activity or an exceptionally high mass-to-volume ratio, both phenomena observed in natural comets. Moreover, while uncertainties about the exact size and composition persist, they increasingly favor a large CO2-rich comet as the best fit for the available data. In contrast, the artifact hypothesis, suggesting the object is an artificial construct, finds fewer supports. No evidence of deliberate maneuvers has been observed. There are no detected technosignatures such as narrowband radio transmissions, geometric structures, or unusual reflections that would point toward an engineered origin. The statistical argument for rarity, positing that such an object should be exceedingly uncommon, remains contested, and most of the anomalies initially noted can now be plausibly explained by natural phenomena. Loeb's score on the so-called Loeb scale has already decreased from 6 to 4 out of 10, and it is anticipated to decline further unless future observations reveal something extraordinary at perihelion. The debris stream hypothesis, proposing that the object is a fragment from a larger catastrophic past event, is inherently more challenging to evaluate quantitatively. Without the detection of associated objects or signatures indicative of a stream, it remains indistinguishable from an unusually ejected comet. The key to validating this hypothesis lies in identifying shared fingerprints, such as similar velocities, compositions, or arrival times across multiple interstellar objects. To assist in this endeavor, a comprehensive observational checklist has been devised for the coming years. Vigilance should be maintained for new interstellar detections announced by the Minor Planet Center. An important factor to monitor is the chemical composition. If multiple objects display a CO2-rich signature, it would constitute a compelling pattern. Likewise, analyzing their velocity vectors can reveal whether several objects share similar directions and speeds, hinting at a common origin, indicative of a potential stream. Clustering of detection times, where multiple objects arrive within a relatively short span, would further strengthen the case for a shared source. Additionally, data from dust impacts recorded by spacecraft like the Parker Solar Probe, which flies close to the Sun, or other missions traversing different regions of the solar system. If a sudden surge in impacts with unusual chemical signatures or velocity occurs, it could be a sign that our spacecraft are passing through a debris stream, an indication that fragments from an ancient cosmic catastrophe are traversing our neighborhood. While no such alerts have been issued yet, continuous monitoring remains essential. The cultural impact of this phenomenon cannot be overstated. Over the past 8 years, 3 interstellar visitors have fundamentally reshaped our understanding of the cosmos and our place within it. Before the discovery of Oumuamua, interstellar objects were considered mere theoretical curiosities, hypothetical bodies predicted by our models but never directly observed. We knew they had to exist because of the physics governing planetary systems, yet the universe had kept their true nature hidden from us. Now, they are undeniably real. We have measured their trajectories, photographed their surfaces, and analyzed their chemical compositions. The sky no longer feels like a distant, isolated expanse. It is a more interconnected, dynamic realm. We understand that objects from other star systems routinely pass through our cosmic neighborhood, a familiar traffic that hints at the vast, bustling galaxy beyond our own. In just a few decades, with advancements in survey technology and observational coverage, interstellar visitors might become a common occurrence, part of the regular landscape of our celestial environment. It's almost as if the universe is gently nudging us to recognize this ongoing interchange. And as we become more accustomed to these visitors, our questions about their origins grow more pressing. Another interstellar object appears on the horizon, prompting us to wonder, where does it come from? Although full normalization of this phenomenon hasn't yet occurred, it is undoubtedly on its way. Policy priorities are shifting accordingly. Planetary defense agencies are beginning to classify interstellar objects as a distinct category, separate from the familiar near-Earth asteroids. Their trajectories differ, their warning times vary, and the strategies to mitigate potential threats must adapt to these differences. Currently, there is no immediate danger from 3I Atlas, as its path keeps it well clear of Earth, more than 270 million kilometers away in December. Nonetheless, the very fact that the conversation is happening signifies a paradigm shift. What if one day an interstellar object were on a collision course? How much warning would we have? Could we deflect it if necessary? These questions, which once seemed hypothetical, are now part of serious scientific and policy discussions. This brings us to the importance of the Loeb scale, a provisional adaptable framework for assessing the likelihood that an interstellar object is artificial. The current number assigned to 3I Atlas is just a snapshot, a reflection of our present uncertainties. Whether that figure is 4, 3, or 2, it is not destiny. As our data improves, so too should our assessment change. Bayesian updating, the principle that we revise our beliefs in light of new evidence, reminds us that scientific understanding is fluid. Intellectual humility is crucial, admitting that we don't have all the answers, and being prepared to revise or abandon previous assumptions when the data warrants it. If 3I Atlas turns out to be a simple comet, then the higher artifact probability assigned earlier was misguided. But asking the question, whether it might be something more, was exactly the right approach. It is essential for science to entertain hypotheses that challenge our expectations, even if they seem unpopular or unlikely. The process of scientific correction depends on brave or stubborn individuals willing to propose testable alternatives. Only through such rigorous inquiry can we distinguish genuine anomalies from natural phenomena. Should future observations reveal a maneuver near perihelion, or long-term tracking uncover subtle anomalies, then it would be prudent to keep the door open to the possibility that this object is something more than a comet. Conversely, if the data continues to align with natural models, predictable outgassing, no signs of artificial control, and chemistry consistent with known volatiles, then the artifact hypothesis diminishes further. Imagine the night sky over Mars right now. A thin atmosphere, rust-colored dust swirling, and aloft, visible to orbiting instruments but invisible to the naked eye. A visitor from another star, perhaps a chunk of ice and rock or something stranger, rushing past at speeds that make our fastest rockets seem stationary. Orbiting spacecraft are tracking it, transmitting data back to Earth, where thousands of scientists and millions of curious minds watch, wonder, and hope. Whether it's a mere stone or a red herring, a comet or a craft, remains to be seen. But what is certain is that we are actively engaged in this cosmic investigation, pushing the boundaries of our knowledge and learning from the universe's most enigmatic messengers. A fragment of a bygone world, or merely another speck in the vast expanse of the universe. We remain uncertain, yet our eyes are fixed, our instruments are active, and our minds are deep in discovery. It is this very pursuit of measurement, of understanding, that elevates tonight, October the 3rd, 2025, beyond a simple celestial passage. This moment marks a pivotal point in humanity's voyage, a small, fragile planet reaching out through its technological extension, its telescopes, its mathematical models, to make contact with something originating from the distant stars. Somewhere out there, concealed in the darkness, the next interstellar visitor drifts silently through the void. Eventually, we will encounter it. Perhaps it will prove to be an ordinary object, a cosmic traveler no more remarkable than countless others. Or maybe it will reveal itself as something extraordinary, challenging everything we thought we knew. But regardless of its nature, we shall be prepared. Our telescopes are meticulously trained. Our models are continually refined. Questions sharpened by insights gleaned from the first three interstellar visitors, Oumuamua, Borisov, and Atlas, drive our curiosity forward. No longer is the sky an empty canvas. It is alive with wandering voyagers, each one a message from the cosmos. And we, as temporary custodians of this pale blue dot, are finally learning to interpret the signs they leave behind. Tonight we observe, tomorrow we await, and somewhere within the streams of data flowing back from Mars, perhaps, just perhaps, the universe is whispering something new, an answer, a mystery, an invitation to look deeper into the vast uncharted depths.